Hello everyone. So in this video I will discuss or rather review a little bit of the basics of special relativity, and the idea is that after this review during this review I will set up the conventions, etc., so that we can easily go into a discussion of relativistic electrodynamics. So with that in mind, with that idea in mind that I want to discuss relativistic electrodynamics, let me review some of the key things in special relativity. I'm sure all of you have already been exposed to this subject. So you have done this very rigorously in your classical mechanics course, but this will be mostly, this lecture is going to be mostly a recap of some of the topics in special relativity. Most of my discussions here, I will be following the book by Landau and Lifshitz, Volume 2. The first two chapters, I find the discussion there to be a great exposition to special relativity. So I will just use some of the discussions there in this lecture. So to begin with, before I start talking about special relativity, let me discuss rotations. So all of you are familiar with rotations. And so if I consider, let's say, rotations in 2 dimensions, there's this x and y coordinate. And if I rotate it by some angle theta, then I land up into new coordinate, x prime and y prime. And then the old coordinate x and y are related to the new coordinates x prime and y prime through this relationship here. Okay, so this you can just geometrically figure out. I was trying to do it here, so I just you can see the steps here. I mean, this is just very basic school level geometry. So with this, you can figure out what is the transformation between the coordinates x and y and that of x prime and y prime. Okay, so the idea is that you consider a point whose coordinates are x and y in this unprimed coordinate system, whereas the same point has x prime and y prime as the coordinates in the primed coordinate system. And then you basically try to figure out what is x and y in terms of x prime and y prime, and this is the relationship that you get. Okay, you can easily invert this relation and express x and y in terms of x prime and y prime just by considering, making theta, go to minus theta. Okay, so that will be the reverse transformation, the inverse of this rotation matrix. Okay, so with that, so this is very familiar to all of you, I'm sure. And but the main point why I'm trying to bring this up is that is to emphasize that this is a particular transformation which preserves distance. That means if you consider the distance, which is x2 minus x1, y2 minus y1, square them and add them, then this is basically the distance between the points x1, y1 and x2, y2, right? So let us choose this x1 and y1 to be the origin for that matter. And then if you choose them to be the origin, then you see that under this set of transformation, the distance, which is basically x2 square plus y2 square, that is invariant, because that is going to be the distance in the primed coordinates as well. So x2 prime, y2 prime whole square, and if you add them, then you can just plug in this transformation here for x2 and y2, and you will see, if you simplify, you will see that it remains invariant. Okay, so x2 prime square plus y2 prime square is equal to x2 square plus y2 square. Okay, so this is basically, in the way I'm saying it, this is like immediately obvious as soon as you say that this is the transformation of the coordinates. Immediately you say that you preserve the idea of distance. Okay, so this obviously all of you are very much familiar with, but you can do also you can do the opposite. You can ask the question, for instance, what are the set of linear transformations that preserves this distance? Okay, what is the set of linear transformation that would preserve distance. This is the infinitesimal version of this distance here. Okay, so if you ask that, what are the set of transformations that would preserve this distance, then the answer to that question will be basically, this is basically the one parameter set of linear transformations where you have this parameter theta. This is all the everything that's possible to write down, which will preserve distance. Okay, so now, I mean, again, there are qualifications to this statement, but this is how you can think about this. Okay, and of course, here I am doing 2 dimensions. You can also very simply generalize it to 3 dimensions. Okay, here you have just one parameter in three dimensions. You will have basically 3 parameters. 3 rotation parameters. So now. Right. Now, with this, you can let us now ask one further question. So this was more or less what I wanted to say about rotations. I will come back to it again when I discuss vectors, covectors, etc. But this was just the introduction and warm up. So what is the idea? The idea is this is a set of linear transformations like this, and it keeps the distance invariant. Okay. And you can use that fact to actually define the set of linear transformations. Okay, so very good. Now, if you now try to ask the question. So this was the transformation that told us what happens if we rotate the coordinate. But what about boosts? Okay, so this word boost means that you have a frame, let's say x and y. Okay, and then you have a primed frame, x prime and y prime. Now you take the primed frame and you start moving it with a constant velocity. So this v is a constant. Okay. So if you move it with a constant velocity, then you can ask that what is the coordinate transformation between these 2 coordinate system. Okay. And this, moving with this constant velocity, this is the thing that I'm calling as a boost transformation. Okay. So if you ask that question, you might immediately give an answer to that, which from what you see from experience, and that answer to you, that answer that you will provide, from experience, would be known as Galilean boosts. So this is what you might do. Let's say you can think about the situation as, let's say you are standing on a platform and there's this train which starts moving with constant velocity. So so now you can ask that what is the coordinate transformation between yourself and a person inside the train. Okay. So here the word constant velocity is important because we are going to consider boost transformations between 2 inertial frames. Okay. So again, an inertial frames, as you all know, is defined by Newton's first law of motion. It's basically a frame of reference where Newton's first law of motion is valid. And the boost, I just mentioned that it's basically a frame of reference which is moving with constant velocity, and that ensures that both the unprimed frame as well as the primed frame both are inertial frames. Okay, so this is basically a question about a transformation between inertial frames. Okay, so now, as I said, if you try to draw from experience, let's say you are looking at a particular point which you can call the origin. So you will see, if you are in frame S, you will see that the origin of S prime is moving with some velocity v, right? And this is not only true about the origin, it's true about any point for that matter, right? So let us say that at time t equal to 0, both the origins of time and space for both the frames S and S prime, the origins coincide. Okay, so if the origins coincide, then you will see that this x prime, this point from the point of view of the S prime, this frame. So this one is moving in this direction with v velocity. So if you are in the S prime frame, then you will see that a point in the S frame is moving in the other direction with velocity v, right? So in that sense, the x prime coordinate of S would get reduced by this vt. So as time increases, the x coordinate becomes more and more negative because a point here is moving on the other side, okay, on this side, okay. So similarly, if you express x in terms of x prime, then you can take this vt on this side of the equation. You will see that, any point here would, like, its x coordinate will keep on increasing with time because it is moving with a constant velocity here. Okay, so this is what you would expect and what you would write down, and you will be correct as long as this particular velocity is very, very much small compared to the speed of light. Okay, we'll get there. That, how this is not true if there is if this velocity is very high, comparable to speed of light. Okay, but these transformations as written, they are known as the Galilean boost transformations. And in this transformation, the y and the z coordinate remains as it is, and so does time. Here you are assuming that the time in both the frames s and s prime, that time is the same time. Okay, you are basically, there is no difference between the ticking of clocks between s and s prime. Only in that case you are you can say this, that the transformation between x and x prime is this. Okay, so this fact that t is equal to t prime is basically an assumption that you are making, and so this is this transformation is called Galilean boosts. Now, as I said, that this is, if I try to list down the features of this Galilean boost, then this absolute time, the absolute time means that no matter what velocity the frame is moving in, there's one absolute time, there's one clock, there's one flow of time which is same for all the frames. Okay, so that is a feature of this Galilean boosts. The second thing is, if this is true, then you would just basically add velocities. So let's say now, if there is some particle here moving with some velocity, let's say u. So let's say in the s prime frame, there's some particle moving with velocity u. Then from the point of view of s frame, this particle will move with velocity u plus v. So there's just addition of velocities as far as Galilean boosts are concerned. You just add velocities. So this is again another feature of these Galilean boosts. Okay, it's just you add velocities, and if you add velocities, then it would immediately imply, let's say in the frame s prime, there is a light wave, okay, or a photon, or however you want to think of it. There's a light wave which is moving with some velocity c. Okay. So if the light wave is moving with some velocity c in the s prime frame, then from the s frame point of view, because velocities add, this light should move at velocity c plus v, right? So therefore it would imply that the velocity of light should depend on the velocity of the source. Okay, but again, as you all know probably very well, such a thing has been ruled out by these experiments of Michelson and Morley. Okay, I'm sure you have learned about this experiment in great detail when you learn special relativity, so I'm not going to get into the details of the Michelson-Morley experiment. But what I want to mention here is that you see that there is experimental evidence that this kind of transformation between two frames which are moving with a constant velocity with respect to each other, this is probably needs some corrections. Okay, of course, if the velocities are small, let's say, as I said, give you the example of a train, you can actually, this is actually, you can verify that. But if you verify that, then you are, if you consider that this is correct, then you are led to certain conclusions for which, also contradict certain experimental observations. Okay, so there needs to be some modification to this set of transformations, particularly when you are talking about high velocities. Okay, so now. So this Galilean boost can't be the complete story, and so as Einstein put it, so Einstein thought about this problem very hard, and he came up with a solution. And the solution that he came up with is the fact that here the fact that we are assuming absolute time, this time is the main suspect here. So Einstein had remarked this, that time is the suspect, okay, in all of this deliberations. Okay, so now the key idea, therefore, is to come up with a principle which would perhaps violate this idea of absolute time, and which will be consistent with observations. Okay, so that is where we come to special relativity. Okay, and also we'll see, as I had repeatedly emphasized, if you look at Einstein's paper, then Einstein was also motivated a lot by thought experiments in electrodynamics, and as we'll see that basically electrodynamics contains, I mean, it is relativistically covariant, so it kind of, Einstein was able to read off special relativity from the known electrodynamics of that time. So basically, but here let us go step by step. So here let us say that I think it is easier to understand if you consider this as a principle, and then we go into a discussion of relativistic electrodynamics. So let us consider the principles of special relativity, which are the postulates, if you like. And the first postulate tells us that the laws of physics are the same in all inertial frames. Now, this word "same" needs a little bit of a clarification. So, basically, if you what is meant by "same" is basically that laws of physics can be expressed as equations. Those are covariant under any transformations such as boosts or rotations. Okay, so just to explain this phenomena, you see, if we consider Maxwell's equation, let's say Gauss' law. For Gauss' law, this is pretty trivial. So for Gauss' law, we know that this is scalars on both sides. This is a scalar, doesn't transform under rotation, and this is a scalar. Okay, so if we rotate our coordinate system, then this expression remains invariant. Okay, because both right and left hand side are scalars. But let's say if we consider the Faraday's law, okay, which is a vector equation. Okay, so if you consider Faraday's law, this is a vector equation, right? So it is not true that component by component, so if we make a rotation now, the vectors are going to rotate. As we saw, the components of the vectors are going to change. As you are aware, what happens in rotation, the vectors, for the vectors, the same thing happens as with the coordinates. Okay, so the components of the vectors are going to change. But this equation, written as a vector equation, that would be valid even in a rotated coordinate system. Okay, so as far as this equation is concerned, because this is written as a vector, therefore this equation is covariant under rotations. Okay, I say covariant because if you consider component by component, the components are going to change. They will get mixed up, of course. But as a vector equation, this equation is going to remain same. Okay, so this is the crux of covariance. Okay, so we have these nice quantities which transform nicely under rotations, and we should be able to express our equations in terms of the vectors. Okay, so as soon as we do that, then we'll be assured that these laws that these equations represent, they are quote unquote same in all the frame of references. Okay, so just to give a counter example, if I said in the Faraday's law, if I said that the x component of this is equal to the y component of the magnetic, let's say that just assume that this was the case. Okay, if I said that, and if I made a rotation, then of course this x component is going to become a combination of, let's say, x and y coordinate, and this is also going to become a combination of x and y coordinate, and then this statement would not have been invariant under rotations. Okay, but because this is this is not so, and we are writing it as a vector equation, therefore we can say that these equations are covariant under Lorentz. These equations are covariant under rotations, And this is what I mean when I say laws of physics are same. Okay, so now we want the laws of physics not only to be covariant under rotations, but we want them to be covariant under rotations as well as these boosts. Okay, by boosts I mean coordinate transformation between two inertial frames, where the two inertial frames are moving with respect to each other with constant velocity. Okay, so I hope that the idea of this first postulate is clear to everyone. Now the second one says that the speed of light in vacuum is the same in all inertial frames. You cannot touch the speed of light. Okay, so it's not that time is absolute, but the speed of light is absolute. That means if light is traveling with a so let's going back here to this diagram. So if light is traveling with velocity c here, so and this frame is moving with velocity v with respect to s, even with respect to frame s, light would still travel with velocity c. Okay, that is the idea. So you see, so this is the second idea, and this is a very key input that will help us do a lot of things. Okay, I mean, this with the help of this postulate, we can build up the whole set of transformations that is consistent with we can build up the set of boost transformations that will that will basically be a generalization of this Galilean boosts, and which will be consistent with observed experiments. Okay, so that's what we will do. So the first important, so there are two steps in this process. So you might have already seen the so-called Lorentz boost transformations, but we will in some sense derive this Lorentz boost transformations starting from this postulate, and maybe a few more assumptions. With that, we will be deriving this Lorentz boost transformations, and that involves two steps. Okay, so the first step in that direction would involve the proving that this postulate implies the invariance of something called an interval. Okay, so this interval I want you to think of as a generalization of the idea of distance. That is why I was mentioning rotations at first. Okay, so the rotations are such transformations that keeps the distance invariant. But here we are going to consider something else. We are not going to consider distance, but a generalization of the notion of distance, which I'm going to call an interval. And I'm going to prove that with this postulate of relativity, okay, with this postulate of relativity coupled with a few more assumptions about space-time, I will prove that this interval must be invariant under Lorentz boosts as well as rotations, under boost transformations as well as rotations. Okay, so what is the idea of this interval now? So the interval, before going into the interval, let me define for you something called an event. Okay, an event is nothing, it's like a fancy word for a point in space-time. Okay, so you have the space coordinates x, y, z. I will again work with Cartesian coordinates. Okay, so let me consider Cartesian coordinates x, y, z for spatial part, and the time. Let's say something is happening at a particular location and at a particular instant of time. That is what we are going to call an event, and this is an event. Okay, a point in space-time. Okay, now given two such events, we can define an interval between the two events in the following way. Okay, so this, if you like, is the distance between the 2 points. Okay, and then you basically take the time, the time difference, multiply it by the speed of light, and square it. Okay, and take the difference of the distance square. Okay, so this quantity is what I'm going to call as the interval. Okay. So you might think that why I am looking at this quantity. You will soon realize why I am looking at this quantity. Okay, you will see the importance of this interval. It's going to be very, very important in what we are discussing. So now let us. So of course this is a finite interval. Okay, so we can define infinitesimal version of it in this way. So where of course this is the ds square. This is a small order 1 So ds is the order 1 infinitesimal, ds square is the order 2 infinitesimal. So ds square, okay, so this is the infinitesimal interval square. Then we have the infinitesimal differences in time and space. Okay, so sorry, here there will be a bracket. So I missed the bracket. Right. So right now here I must say that whatever I'm going to discuss is independent of the relative signs. So I could have put a minus sign here and a plus sign here, a minus sign here and a plus sign here. Okay, that wouldn't make any difference in my discussion. This sign, overall sign of the interval, is a mere convention, and basically we have our own conventions in which we work in. It's not going to change any of the conclusions. It doesn't affect any of the physical conclusions. Okay, so you will see some books use this opposite sign for the interval, and whatever I'm telling you, I'm just being consistent with some of the conventions in the books that I have recommended, like Landau, Lifshitz, or Griffiths, and books like that. So therefore I'll stick to this convention, but this is also another convention, and by the way, this is my favorite convention. But again, for the sake, so that you can follow the discussions there as well, I will basically stick to this other convention. Okay, so basically you see that this in this ds square, the distance is already there between the 2 points, between the locations of the event, and also the time difference between the 2 events, that also comes in. Okay, and then there is a relative minus sign between the two. Okay, so this is the idea of an interval. And so why am I discussing this? I'm discussing this because I'm now going to argue that given the postulate of relativity, this universality of speed of light, this idea can be used to show that this interval is invariant, or must be invariant, under let's say a boost transformations between two inertial frames. Okay, so that is my objective. So in order to proceed, let us first make the following observation. Okay, so the first observation is that the universality of the speed of light tells us that if the interval is 0 in one frame, it must be 0 in all other frames. So again, remember our 2 frames, S and S prime. Okay, so S and S prime. So S prime is moving with velocity v. So even if it is moving with velocity v, this interval should be, if it is 0 in S prime, it must be 0 in S if the velocity of light is the same in both the frame of reference. Okay, so why is that true? As you can see that if I say that this is the basically in time del t, this is the distance that is covered between light. So consider 2 points, let's say light starts from one point and reaches another point, and this is the distance between the 2 points, right? So in one frame, the interval is basically, let's say the time t1 and t2. That's in one frame. Okay. Then basically this distance d divided by t2 minus t1, that's basically c. Okay. That's the speed of light. Okay. But if you consider the same 2 events from the other frame, t2 minus t prime has changed because this has become t2 prime and t1 prime, and so must the distance. Okay. So such that the speed of light is same. Okay, so that it has to be the case, and if that is the case, then this difference between the distance covered between the 2 points and the c squared times this time interval, that must vanish. Okay, so it is a this fact is a consequence. It's just a consequence of the fact that speed of light is same in both the primed and the unprimed frame of references. All right. So this is the first deduction that we have, that if ds square is 0 in one frame, then ds square is 0 in all other inertial frames which are moving with constant velocity with respect to the previous one. Very good. Now let us consider, if this is the case, then it immediately follows, something immediately follows. And that something is basically, it tells us that ds square and ds are proportional to each other. Why am I saying they are proportional to each other? Because you see, ds squared and ds prime squared, these are infinitesimals of same order. Okay, so of course, if they are infinitesimals of each of same order, they need not be proportional. There can be some other constant b. Okay, there can be some other constant b. But if ds is 0, then we know that this thing must be 0. So this b must be equal to 0. This constant cannot appear in this relation. And because they are infinitesimals of same order, they must be proportional to each other with the proportionality constant a. Okay. And so what do I mean by this is very simple. That, if I say that ds squared is some function of ds prime square, then I can, because this is infinitesimal, I can expand it in a Taylor series expansion. And basically what I'm saying is, of course, this is a second order differential. Okay, so treat this as the same order differential. Okay, then the constant part must be 0, because there's this condition that whenever this is 0, this has to be 0. And all higher order terms, they are negligible because they are infinitesimals. Okay, so that's how you can think about it. Okay, so basically what we conclude is, the postulate of relativity tells us that these two intervals, infinitesimal intervals, must be proportional to each other. Now, once the infinitesimal intervals are proportional to each other, then we can this proportionality constant in general can depend on various properties of the two frames, right? It can depend on, for instance, the two coordinates in the two frames, like x prime coordinates here, this one. It can depend on the velocities and the velocity direction and the velocity magnitude. Okay, the velocity being the relative velocity between the prime framed and the unprimed frame. Okay, so but, I'm so sorry. Yeah, so but we see, now we come up with two more assumptions about space-time. The first assumption is that assumption of, called homogeneity of space-time, by which we mean that no point in space-time can be special. Okay, all points are equivalent. Okay, so if we are in a homogeneous space-time, then this is this constant cannot depend on the coordinates. Okay, they cannot depend on the coordinates. Of course, you can say that there can be various objects in space-time, and of course, we can treat them like we can account for them. But this is the case where I'm saying that consider a space-time which is homogeneous and equivalent at every point. This is just a background space-time, so basically the physics cannot depend on where you are doing it. Okay, so all the points are equivalent, and therefore this proportionality constant cannot depend on the coordinates. Okay, similarly, you can say that there is another assumption that we can make about space-time, which is isotropy of space-time, by which I mean that you look at any direction, all the directions should be equivalent. Okay, so again, so this is like an assumption about the background space-time, on which of course something can happen, and because of that some points can be special, or there can be special directions. But as far as the background space-time is concerned, on which about which we are talking about, that has these two properties. If we assume them, that has these two properties, again, let me say that sometimes if you are doing a discussion of general relativity, there can be objects that distort space-time, and then this assumption is not right, and then we have to treat it in a different way, in a special way. Okay, which again we are not discussing here. We are talking about a space-time where this assumption is valid. So if this particular assumption is valid for a space-time, then we can say that this A, because it's isotropic, then it immediately follows that this A cannot depend on the direction of the velocity. because if it did, then basically, that would break the idea that, a direction would become special, and it would break the isotropy of space-time. Okay, so these two things are something that I'm assuming for the space I'm trying to represent in both the coordinates, like s and s prime in both the coordinates. Okay, this should be true, and therefore we will have this A can only depend on the magnitude of the velocity. It cannot depend on the coordinates. It cannot depend on the direction of the velocity. Okay, so we can say that this relationship A can be only the magnitude of the relative velocity. Okay, it cannot depend on the direction of the velocity. Okay, so very good. This is the thing that we have just deduced, starting from the postulate, that means universality of speed of light, and these two assumptions, homogeneity and isotropy. Okay, that leads us to this fact that the two infinitesimal intervals in the two primed and unprimed frames, they are related by a proportionality constant which can depend on the magnitude of the velocity, relative velocity between the two frames. Okay, so now further, let us give further arguments. Let us say that, well, if this thing is non-zero, this A is, not equal to 1, if this A is not equal to 1, then of course this interval would not be invariant. Okay, because then in one form, this interval is something, in the other frame, depending on velocity, the interval is something else. Okay, so therefore, let us see if we can say anything more about this proportionality constant A. So in order to do that, now consider three frames, S, S2, S3. Okay, maybe I can change it to S1 and S2. That's what I have done here, S1 and S2. Okay, so right. Okay, so now we can use this. So the relative velocity between S and S1 is V1, and the relative velocity between S and S2 is V2. Okay, so maybe it's also worthwhile to write that down. So this relative velocity is V1, and this relative velocity is V2. Okay, so then from the previous conclusion, we will write that ds square, this is in the S frame, is equal to a V1, magnitude of V1 times S1 square, ds1 square. Okay, it just follows from this conclusion. Similarly, with considering S and considering S, so this I'm considering S and S1. This I'm considering S and S2. So therefore, this is magnitude of V2. And now, if I consider S1 and S2, then I will have this will be the magnitude of the relative velocity. I'm sorry. This will be the magnitude of the relative velocity between S1 and S2. Now, that relative velocity, what it is, or what is the rules for addition, we don't know. But this is definitely going to depend. This is definitely going to depend on the relative angles between V1 and V2. Okay. So for instance, if they just added, even then this magnitude is going to depend on the relative angle between V1 and V2. Okay. So so this object here is the transformation of the interval between S1 and S2, which is the relative velocity between V1 and V2. Okay, sorry, which is the relative velocity between S1 and S2. Okay, it's proportional to the magnitude of that. So with these conclusions, we see now we can take ratios of these equations. Okay, I can take a ratio between this one and this one. Okay, that will give me this side. Okay, and this ratio is going to tell me that let's say this thing divided by this thing is basically equal to ds2 by ds1, but that ds2 by ds1, I know that this is given by this a of v1 v2. Okay, I'm just taking the ratio and substituting ds2 by ds1 using this relation. So if I do that, I will get this relationship in terms of the proportionality constants, which can depend on the magnitude of the velocities. But if I write it this way, as you can see, the left hand side, the magnitudes of v1 and v2 only enter, and their relative angles does not enter. But on the right hand side, the magnitude of the relative velocity between s1 and s2 enters, where of course the angle between v1 and v2, that is going to enter here in this thing. Okay, so if this enters here, the angle between the two velocity enters here, then we would think that this relationship cannot be true, because the left hand side does not depend on the angle between v1 and v2, and the right hand side depends on the angle between v1 and v2. Okay, so this cannot be a possibility, so we are led to something like a contradiction. But you see, there is one possibility which will get us out of this problem, and that possibility, and there's just one possibility, and that possibility is that if these A's are independent of the magnitude as well. Okay, so if the A's are independent of the magnitudes, then you see, then this equality can be valid. And if the A's are independent of the magnitude, then it also immediately tells us that A must be equal to 1. Okay, so you see, in this way, just by a set of arguments, we are able to conclude that A must be equal to 1. Okay, so A must be equal to 1. And if A is equal to 1, then it immediately follows that the intervals in both the S and S prime frame, where the two frames are moving with respect to each other with velocity v, the intervals, the infinitesimal intervals, must be the same in both the frames. Okay, so this is like, as I mentioned before, this you should think of as like saying that the idea of distance is invariant under rotations. So under a boost where frames are moving with respect to each other with constant velocity, the interval must be invariant. Okay, and that is a direct consequence of the universality of speed of light, which is a postulate of the principle of special relativity. Okay, so with this was like our step 1 for this thing. As an exercise, you can try to show, although you can show it in various ways, you can try to show that, if this is the case, then the idea of simultaneous event, that becomes a relative concept, which means that, if there are two events that are simultaneous in one frame, okay, simultaneous meaning their dt is equal to 0 in one frame, then in another frame they need not be simultaneous. Okay, if this has to be true, if this interval has to be invariant, then it is a direct consequence of that simultaneity becomes relative. Okay, this you can immediately show, just 2 words from here. Okay, so right, so good. So now the next step, once we have shown that the interval is invariant, now we can use that. So you see, the postulate of relativity, which is the universality of speed of light, tells us that this interval must be invariant, and that can now be used to work out the right set of transformations between two inertial frames that are boosted with respect to each other with a constant velocity v. So under boost transformations, we need to have this kind of a interval. So assuming that, so of course this is an infinitesimal statement. Now you can integrate the infinitesimal statement to convert it into a statement for finite difference or finite intervals. Okay, then also this should be valid. If it is valid for all infinitesimal intervals, then it should be valid for finite intervals as well. Okay, so yeah. So therefore, now again, if one of the origins of this finite interval, or one of the points of this finite interval, or one of the events is the origin of space-time, then and we assume that in both the frames the origins coincide. Okay, so that point is common for both the frames. Then we can say that for any point in S and S prime, okay, in the s and s primed coordinate, we should have this expression to be valid. Okay, this is like a generalization of the constant of the concept of distance. And if you like, you can put a vector here. Okay, that's what I mean. Okay, in 3 dimensions and in 2 dimensions. So this x is a representative. So x is the direction along which you are boosting. That is like a special direction. Okay, so now we want to keep this invariant. We want to write down a set of transformations for which this remains true between the primed and unprimed coordinates. Okay, so we want a set of transformations for which this is true. And if you remember, our distance was essentially something like this, very similar, but with a plus sign, right? When we said this is x prime square plus y2 prime square, then there was a relative plus sign. The only difference now is that there's a relative minus sign. And how do you write down a transformation in, let's say, now we can consider just one direction. Let's say just consider x for simplicity. So if you consider just x, one direction, one of the spatial directions, then that is the one that takes part in the transformation. The other 2 coordinates, if you like, they are just spectators here. You can say that y equal to y prime and z equal to z prime. Okay, these are the, if you like, spectator coordinates. And the transformation is really happening between time and the spatial coordinate along which the boost is being this boost is occurring. So if you look at this diagram here, again, this v is directed along the x direction. Okay, so that is the reason why there's a mix between x and t. We already saw in the Galilean case that x and t got mixed, but now we are trying to do it properly. We want to respect special relativity, so we want to do the transformations in such a way that this interval remains invariant. And as you will see, the most general linear transformation that you can write down to keep this interval invariant is basically this set of transformations where the cos's and sines has been replaced by cosh and sinh, because these are the corresponding hyperbolic functions, and because it can deal with the sine very efficiently. Okay, and also you see there's no relative sign here. There's no minus sign here. Okay, this is cos sine, sine cos, or cosh sinh, sinh cosh. Okay, had it been rotation, then this would have been sine and there would have been a minus sign here. Okay, so that this difference makes it work, because you see, if I start with c square t square minus x square and then substitute this thing here, okay, you see, if you follow the algebra, then you see you will have a cosh square minus sinh square here in ct square, ct prime square. Okay, that is going to give you 1. And similarly, you will have a sinh square minus a cos square for x prime, okay, which is going to give you a minus 1. Okay, and the relative cross terms, they cancel between the 2 things. Okay, so there's going to be a 2ab term, like this is like a plus b whole square. So that mutual, the cross term, that cancels between these 2 expressions. Okay, so that's how this interval is invariant if we choose the transformations in this way. Or these are the set of transformations that keeps the interval invariant. Okay, it is also a 1-parameter set of transformation parameterized by this parameter psi. Okay, unlike this is not sinh and cos, so this is not sine and cos, but this is sinh and cosh. So unlike that, this is not an angular coordinate. Okay, but this psi is a 1 parameter that parameterizes the set of transformations, okay, which keeps the interval invariant. As we will see that this parameter can be thought of essentially as representing the velocity. So of course we can boost with various velocities, and those that velocity gives us a 1-parameter set of transformations between 2 inertial frames which are moving with constant velocity with respect to each other. The value of the velocity is a parameter, right? So we will see that this psi is determined in terms of that relative velocity. Okay, let's see how that happens. So in order to do that, let us first observe that if we, let's say, now consider this again, the same setup I have, the primed and the unprimed coordinate. The primed coordinate moving with velocity v along the x direction, in this direction, positive x direction. So now if we consider this s and s prime, we will see that, I'm assuming that the origins of space-time coincide in the two frames. Okay, that I'm always considering. Okay, so if I do that, then I will see that if I consider the origin of, let's say, s prime, okay, then the origin is moving with a velocity v in this direction. Okay, because it is moving with a velocity v in this direction, therefore, if I consider the x coordinate of the origin in the s prime origin, okay, so the s prime origin, let's consider the s prime origin. So the x prime spatial origin, that is x prime equal to 0, that is the x prime spatial origin. Okay, let's consider that point x prime equal to 0. Okay, if I consider the point x prime equal to 0, then that point is moving in this direction with velocity v, because it is in the s prime frame, and therefore its x coordinate in the unprimed frame must be, that divided by the time. Okay, the time at which you are calculating it, that should be the x coordinate, or simply the x coordinate should be equal to v times t, because x prime, this is the x prime equal to 0 point. Okay, this is the same kind of considerations which we use to write down the Galilean boost. Okay, so therefore this fact is just true, that for the origin x prime equal to 0, okay, x must be equal to v times t. Okay, or rather v equal to x by t. Now, the interesting thing is, if we go back to this set of transformations, and if we substitute that x prime equal to 0, then we get this expression. Okay, I've just substituted x prime equal to 0 because that is the point I'm looking at. Then it reduces to these two expressions, ct equal to ct prime cosh and x equal to ct prime sinh. These are the coordinates of the origin in the prime coordinate. Okay, of course, this point, that exists at different values of time. So, that exists at different values of t, t prime is there. Okay, so for those different values of time, we can write down this expression for the coordinates as far as the s frame is concerned. Okay, I hope this is clear. Now we can take a ratio of this. If we take a ratio of this, we can write down sinh by cosh, this thing. Is this tan psi. Okay, this is equal to x by ct, as we can see, because this t prime cancels. Okay, if we just take the ratio. Now, as you can see, because I concluded that x by t for this particular point is v, therefore I can just say that x is basically v times t, and this ratio therefore is just v by c. Okay, because I am looking at that particular point. Okay, the origin of the s prime coordinate. Okay, so therefore I have tan psi equal to v by c. This v by c is going to occur so many times that it is given a special notation. It is called beta. Okay, so every time I'm going to denote beta by this v by c. Okay, this is very important. Okay, this notation. Okay, so v by c will occur everywhere in our discussion, and it's nice to give it a name. Let's call it beta. So now if tan psi is beta, then we can immediately find what is sinh psi and cos psi. Okay, in the usual way, using the relation between sine and cos and tan. So if we try to, essentially we write down this is by sinh by cos, and then express cos in terms of sinh and solve for sinh. That's the idea. So if you just do that, you will get this relationship of sinh psi and cos psi. Okay, this is given by beta by 1 minus beta squared to the half, and this is like 1 by 1 minus beta squared to the half. Again, this factor occurs so commonly in our discussion of special relativity that this is also given a name or a notation, and this is called gamma. Okay, so wherever gamma appears, gamma is inverse of 1 minus beta squared to the power half. Okay, so it's 1 minus beta squared to the power minus half. It's the inverse of this quantity. Okay, so basically this is the this is gamma. So if I now write the sinh and the cos. So this is just gamma, if you like. This is just gamma, the gamma times beta, and this is just this is just gamma. Okay, cos is just gamma. So I can just take this and plug it back in this expression of the transformation, and then I have this set of transformations. And this, as you may have seen many times before, is your beloved Lorentz boost transformation. Okay, this is the transformation which is consistent, therefore, with the postulate of relativity, and it relates the coordinates in the two frames which are moving with a constant velocity v in the x direction. Of course, again, it's true that y prime is equal to y, or y equal to y prime. Let me write it that way because I'm expressing it. And at the same time, z equal to z prime. Okay, that is definitely there. Okay, because there is no boost along those directions, these coordinates are unaffected. Okay, so we can also take this transformation matrix and invert it and write x prime in terms of write the primed coordinates in terms of the unprimed coordinates. So if I do that, then I will, you can find the matrix and take the inverse, you can do that. But then there is a simpler way to do it. You just take the velocity and reverse its direction. You just take v2 minus v. Then whatever you will get is basically going to be the inverse. It has to be the inverse. You can check this. You can find that the inverse transformation is basically this. By inverse transformation, what I mean is that here you have x prime and t prime. You just solve for x prime and t prime in terms of x and t. Okay, using these two relations. Okay, so if you do that, then you will find that this is the case, and you can avoid the algebra just by noticing that if s prime is traveling with respect to s in this direction, then s is traveling with respect to s prime in the other direction with the same velocity. So you can just change the sign of velocity to get this. Very good. So this is the overall full set of Lorentz transformations that we have. And right. So yeah, I have mentioned this, and this transformation keeps this interval invariant. You can check it again algebraically. You can put this in, and you will see that it keeps this invariant. We have to check this in terms of the cos and sinh, but you can also check it in terms of the gammas and betas. So we have done this already here. You can also check it in terms of the gammas and betas. Okay, very nice. So at the end of the day, we see that we have 3 independent rotations, and we have 3 independent boosts, which are like along the x, y, and z direction, and these are the these are the rotations plus boosts. These are the so-called Lorentz transformations. It's the complete set of Lorentz transformations. Okay. So when I'm talking about boost, I call it Lorentz boost. Okay, this is a transformation for a Lorentz boost along x direction. Okay, so similarly, there can be a Lorentz boost along the y direction and a Lorentz boost along the z direction. Okay, so these are 3 different boosts that are possible. So similarly, there can be rotations also. Okay, like rotations along the xy plane, and the other planes. That would basically tell us that these are the various transformations that we can combine together to form the so-called Lorentz transformations. Okay, so yeah, I mean there's a very interesting group theory behind it which I'm not getting into, but essentially this forms the so-called Lorentz group. Okay, so right. I want to mention one thing which is very important, and so if I look at this structure of this the way I have defined the interval, you see this combination of the distance is there in the interval. So if we rotate the coordinates x, y, and z, then this combination is going to be respected. This will be invariant because, as I said, rotations keeps distances invariant. You know that. So therefore, this particular interval is not only invariant under Lorentz boosts like this, it is also invariant under rotations. Okay, so if you have if you now consider these, so this interval therefore is a generalization, as I keep on emphasizing, of the concept of distance, and which is invariant under both boosts as well as rotations, and so this is a very, very important quantity that we can use. So yeah, so now right, so right, so so this is again very central. So as we said, that this is something which helped us arrive at the right set of coordinate transformations between two boosted inertial frames. Right. So you can use this idea, now that we have found Lorentz transformations, you can use Lorentz transformations between two inertial frames to do these physical effects that you have. You can find the so-called length contraction. You will see that there's something called a proper length. That means when if you consider a rod and you try to measure its length, then if you measure it while it is moving, then that length is going to be different from the length if it is at rest. So the length of the rod when it is at rest is called the proper length, and that is denoted by L0, and that is related to the length when it is moving through this relationship. And as you can see that there's a length contraction. This object here is definitely going to be less than 1, because v, the maximum speed of light is, so the maximum value of v is c. So so this object is definitely going to be less than 1. So the length would be maximum in the frame where it is so it is so it is maximum in the frame where it is at rest, and if it is moving, then it would appear smaller, and that's why we call this length contraction. Okay, so right. Right, so you can also try to use this to find the relative addition of velocities. So let's say, there are two velocities. Let's say a particle is moving with velocity v in the s frame, and it is moving with another velocity v prime in the s prime frame. Then you can try to find the relationship between v and v prime, just using the fact that, dx dt and dx prime dt prime are the two velocities, and use the basically the Lorentz transformation and the invariance of the interval to figure it out. This you have probably already done in your previous special relativity course, so I'm not getting into much details about this, but you should try to sit down and work it out if you haven't. Okay, so with this, let me go into let me go into a discussion of something called proper time. Okay, so right. If we now, let us consider a clock in the s prime frame, okay, which is moving with some velocity v from the point of view of the s frame. Again, please remember that diagram that that I had. This thing, this is always going to be my convention when I'm talking about frames. So, right. Let me paste it here. Yeah, please remember this diagram. So here s prime is moving with velocity v. Let's put a clock in s prime. Okay, so that the clock is moving with respect to frame s with velocity v in the plus x direction. Okay, so now in the s prime frame, the clock is static. and therefore it has a given location. So in the S prime frame, the if you consider, because it is at the same location, so the dx prime for the clock, that is equal to 0 for in the S prime frame, because it is at the same location. Its location doesn't change, but it ticks. Okay, so its time is changing. Okay, so in the S prime frame, the interval between two ticks of the clock is therefore just given by c squared dt squared, because it is happening at the same location. Therefore, dx square is 0. Okay, so this is the interval from the S prime frame point of view. What about the interval from the S frame point of view? Okay, let's now try to look at the interval from the S frame point of view. So in the S frame, the two events of the ticking of the clocks, okay, they are separated by a distance, and this distance is going to be like this is, if this is the distance squared, then this is like v squared dt squared. Okay, so there are two ticks of the clock. Let's say it starts from here and it ends here. So then the first tick, these are the two events where consider two ticks of the just one tick of the clock, like it starts and ticks. Okay, so the first event from where you start counting is this point, and the second point is this one. So there's a distance from the S frame point of view. Okay, because the clock is stationary in the S prime, but it has moved. Okay, in time t it has moved a distance. So that distance is basically v times the time that the clock shows. Okay, so if that is the case, then this distance is simply given by the relative velocity v squared times dt squared. Okay, this distance square is given by v squared times dt squared. Okay, so now if we consider the interval, so this is c squared d prime squared. This is the interval from the S prime point of view, and this is the interval from the S frame point of view. And this distance we know now is basically v by this is basically v squared. This is basically v squared times dt squared. So if I substitute this as v squared times dt squared and take the dt squared outside, then I will be left over with this expression, right? So this is like, so I'll be left over with, so this is like v squared by c squared, and then if I take the square root on both sides, then t prime would be equal to dt times this factor, and we know this, what this factor is. This is like 1 over gamma squared. This factor we have called 1 over gamma. 1 over gamma. So you see that this is the case. Okay, so now we see that moving clocks, this is the time for the moving clock. Okay, and this one will be slower compared to the this thing. What do you call this? This is the proper time. Okay, this is what I'm going to, this is the time measured in the frame where the clock is stationary. Okay, this is time measured in the frame of the clock, and this is the time measured in the when the clock is in motion. Okay, so the same interval dt prime, okay, is given in terms of dt, okay, multiplied by this factor. Again, this factor is always less than 1. Okay, because this factor is always less than 1, so the same time interval for this, this object is going to be more than this. So the moving clock would turn out to run slower compared to the stationary clock. Okay, so that is why that is just a consequence, if you like, of this invariance of interval for moving clocks. Okay, so now I must say that you can take this, so this time where the clock is stationary, this thing is called the proper time. So you can associate a proper time even with a moving particle. Let's say a particle is moving. You can think of a clock attached to the particle, and that is recording its time. And that time is going to be different from the time of a frame where we are seeing the particle is moving. Okay, because because of this fact of special relativity, that time is a relative concept, or time interval is a relative concept. Okay, because of that, and that follows from the fact that the invariance of the interval, that is something which follows from relativistic postulates. So that you see, because the interval had to be invariant, therefore time had to be, time intervals have to be relative. Okay, as we see here, and therefore we see that that moving clocks run slower. And now we can take, let's say, a particle which is moving. So the particle has a different time from its own point of view compared to that when it is moving. So let's say if you have a subatomic particle which is a finite lifetime, and if it starts moving with relativistic velocities, then we will see that the lifetime of the particle will increase, because it is a moving particle. So therefore moving clock will run slower, and therefore the particle's lifetime will seem to increase if it is moving with relativistic velocities. Okay, so this is the idea in which, and therefore the actual lifetime of the particle when it is at rest, that is basically that time of the particle which is monitored from the frame which is at rest with respect to the particle. It is called the proper time of the particle. Okay, so this time, which is the time in the rest frame, that is called the proper time of the particle. Okay, so right now you can take this. Let's say some particle is moving. It can move even with time dependent velocity. Okay, then you can take like individual segments for which, let's say, the velocity is constant, and then perform this this go to define proper time, and you can integrate it from like infinitesimals to infinitesimals, and you will find that this expression is going to be the expression for a finite difference in proper time. Okay, so this, as you can see, I can take this, because I can take this expression and integrate, and this is like an infinitesimal expression. Okay, it's valid at every point on the trajectory of the particle. Okay, so infinitesimal distances in the trajectory of the particle. Okay, so as if there is a different frame, if velocity is changing, then as if there is a different frame. Okay, so of course these are like different. If it is accelerating, then there is no direct frame transformation to a relativistic frame. Okay, where it is at rest. But for individual small time scales where it is given, you can assume that the velocity is constant. In those frames, you can go to you can do a transformation of frames, and then from there you can integrate that to know the proper time of the particle. Okay, expressed in terms of the time measured when it is like moving with some velocity v. Okay, so I hope that this idea is clear. I think most of you are familiar with this idea. So now there's one small thing about nomenclature, and as I said, that this sign of this thing is a convention. Okay, this sign is a convention, but you can say that these names are used to denote to what kind of interval we are talking about. Okay, so if in our convention, if d square is greater than 0, okay, then this term is greater than this term. Okay, then it is called a time-like event, time-like interval. Okay, if it is less than 0, it's called a space-like interval, because this one is greater than this. Okay, so therefore it is called a space-like interval. And if it is equal to 0, where this cancels this, it's like 2 points between, let's say light has traveled between these 2 points. Okay, so so if we consider that it, at some particular time, light starts from a point and reaches another point at a particular time, these two events are always separated in such a way that the interval is equal to 0. We have seen that, right? So this kind of things are called light-like intervals. Okay, so again, if we use a different convention for here, compared to previously, then we will just say that this is less than 0 is time-like, and this is greater than 0 is space-like, and equal to 0 is light-like. So these words time-like, space-like, light-like, they are very physical. Okay, and so that irrespective of the sign, we will decide whether an event is this thing. And so the fact that whether two events are time-like, space-like, or light-like is independent of this overall sign convention. Okay, so we use these names are used and they are very useful to refer to objects. Okay, so that was like more or less a review of the basics. And now we turn to something which is going to be very important for our discussion of electrodynamics. So we turn to the idea of vectors, covectors, tensors, and metric. Okay, so this this is you have encountered these objects before, but here we are going to say this in a slightly formal way. Again, my objective is just to give you a little bit of working knowledge. I'm not going to get into too much details about the deep mathematical structures behind these ideas. But again, my objective is just to give you a little bit of a flavor of the working knowledge that you would need to understand the structures in electrodynamics. Okay, so again, this is like very brief, and this is the amount that would be this is the least amount that would be essential to continue into the next discussion. Very good. So let's consider rotations again. Okay, so we know that this is the rotation and this is the inverse rotation. Again, inverse rotation is just setting theta to minus theta. Okay, that's what it is. And so now if we consider the infinitesimal transforms, okay, so you just see how dx prime and dy prime transforms, then you would write down a relationship like this, right? Okay, the prime, again, so at some point I'll use, the prime and the bar interchangeably because this prime is hardly visible. Okay, so maybe you can use a bar here instead of a prime, just to make it more visible. But you see, if I, this is just a fact that this infinitesimal object, if I view the x primes as a function of x, then I can write this infinitesimal as a derivative of x prime with respect to x and then dx. Okay, this is just a fact with the differentials. And if we just execute it on these transformations, then we'll see that the infinitesimal has this form. Okay, where these coefficients are precisely the coefficients that appear here. Okay, because this is a linear transformation, this is super easy to do. Okay, so this is how you would say, this is how the infinitesimal coordinate changes, this is how they transform in the primed coordinates to the unprimed coordinates. Okay, now let us ask the question, what happens to the derivatives? Okay, so if I ask the same question, what happens for the derivatives, then you see I have a del x prime here. This one I will write as del x del prime. So here I'm thinking of, let's say I have a function of x prime, then I can differentiate that with respect to del x prime. But now if it is instead of a function of x prime, I consider this kind of a relation and think of this as a function of x prime and x. Okay, then I can write the following thing down, right? This is just basically, chain rule. I now think of this as a thing. I want to convert these two, derivatives. So if I want to do this conversion, then del x prime is del x prime, del x, and del x prime, del y. Okay, where now I have to consider the x as a function of x prime and y prime to know these objects. Okay, but as you can see, there's a difference here. The difference is that there's a sign difference here because the inverse matrix, that is different. Okay, so the sign changes here. But you see what happens if I do a del x prime. So if I take this del x prime, then I get a cos theta here. Okay, I get a cos theta. But if I do a del x prime, then I get a sine theta here. Okay, so this is cos theta sine theta. Similarly, for the y, del y prime, I have a del x del y prime here. So this one gives me a minus sine theta from here. Okay, and this del y prime, that gives me a cos theta. Okay, so you see, then the derivatives transform in this way, in this simple way. Okay, so please pay careful attention to the prime. So the prime is here, the prime is here, and this is just a variable transformation as far as derivatives are concerned. Okay, we do it this way, right? So if we do it this way, then you see, then you know what happens is the infinitesimals as well as the derivatives we find they're transforming in the same way, because this is also cos sine minus sine cos, this is also cos sine minus sine cos. Okay, they're transforming in the same way. Okay, under this rotations, because they are you know, they are going to transform in the same way. Therefore, we don't really distinguish between these two transformations when we talk about you know, rotations. Okay, so you see, now we are going to set a notation. You know, let's set a notation so that visibility is better. The S prime objects I'm going to denote with a bar. Okay, so here, for instance, I mean, for x prime would be my x bar, and y prime would be my y bar. Again, you know, quantities in the prime coordinate I'm going to denote by a bar. Okay, from now on, just so that, you know, it's easier to write. You know, the prime is sometimes not visible, so you know, I'll just switch a convention here. So I'll just write it in terms of bars. Very good. So now you see, here now I can take an object, okay, and I can, if I find an object which is transforming as dxi, okay, this infinitesimal differentials, okay, then I will call such an object a vector. Okay, so if I have an object which transforms as these differentials, then I'll call such an object a vector. And if I have another object, purposely I have written the index down compared to this one, okay, whose components transform as the derivatives, okay, this object I'm going to call a covector. And as we know that for rotations, as we just saw, there is no difference in which the infinitesimals and the derivatives transform. And therefore, it doesn't matter whether I'm talking about a vector or a covector. You know, I can just, you know, it's the same thing. It transforms in the same way. Okay. So it doesn't matter whether I write the index up to write a vector or, you know, write the index below to denote I mean, you know, both of them transform in the same way as we just saw. You know, the differentials and the derivatives transformed in the same way as far as rotations are concerned. Okay. So therefore, this distinction is not so important as far as rotations are concerned, and we have not done this distinction so far. Okay. So anyway, so you can always think of this object as a matrix, right? Okay. So this is I going to j, and there's a matrix I and j. Okay. So this is like a matrix multiplication of a let's say a column vector. Okay. So this is like a 2 × 2 matrix for rotations. And that matrix is simply given by this one. Okay, if this is dxi, okay, and this is the same matrix as we saw for the covectors as well. For the derivatives is the same matrix. Again, I have a I here and I have a j here. So this matrix is the I index first and the j index second, because I am doing matrix multiplication here. Okay, so this b I am treating as a column vector, and this lambda is a row vector. And that gives me this B here. Okay, that's how I'm treating it. And therefore, as far as this matrix is concerned, I'm not careful with writing it up or down, because this, when I'm writing it this way, I'm just concerned with a matrix multiplication. And therefore, my convention is to write the row of the matrix first and then the column. You know, that's how I, you know, identify the components of the matrix. You know, row first, column second. Okay, the usual thing. And then here, this is where, you know, if I write it this way, then this is from where I read of the lambda. But here, as you can see, I have respected the upper and lower nature of the indices. But as I mentioned here, you know, it's not really important for rotations to, you know, maintain the difference. Okay, but just to, you know, point out one very interesting fact about this matrix lambda. So if you just take a transpose and put the sign here and take there, you know, this thing and, you know, interchange. So if you take a transpose, then what you immediately get is the inverse lambda, because, you know, that is the same thing as theta going to minus theta. Okay, that's the inverse rotation. So that's the same thing as inverse lambda. Okay, and basically, you know, if I write it out in components, then if I write the transpose, therefore this statement can be expressed if I take the transpose and matrix multiply. So this I is same, and I have used Einstein's convention. So there's I is summed over, right? So this is matrix multiplication essentially. Okay, so if I multiply these two matrices, then I get the identity matrix. This is just saying that, if I take the inverse and I multiply with this thing, I'll get the identity matrix. And the inverse is basically the transpose. So this is a property of the lambda matrices that implements the rotations. Okay, so this is some property. And I have defined for you in this case what are vectors and what are covectors. And there is no distinction between the way they transform. This we noticed. Very good. Now, right. Why is this deleted? Right. So now let us consider in this thing, let us consider this quantity AI, which is a vector, and BI, which is a covector. And let us, this is a summation convention applied, Einstein summation convention. So there is a sum over I. And by the way, this I travels from 1 to, here it's just 1 and 2. And in general, you can do a general rotation and then it can go from 1 to 3. Okay, so I'm talking about the spatial part. Okay, this I denotes the spatial indices. These are the spatial indices, so to say. Okay, so this, if I do a transformation with the matrices, this is lambda ij, aj, and then there's a bi. This is going to be bik. Bk. Okay, this is going to be bik bk, and now you see that this thing here is I, and this thing here is I, which is supposed to be summed over, but this is not how you sum matrices or multiply matrices. So if you want to think about matrix multiplication, then you have to bring the I on this side and therefore take a transpose. Okay, and so this is basically matrix multiplication with the transpose of lambda. Matrix multiplied with the transpose of lambda, it is written out in components in this way. Okay, so just to write that in the right order, I have written, taken a transpose on this here. Because I have taken a transpose, I could exchange my coordinates, like exchange my indices, because I have taken the transpose. And now this is the way in which matrices multiply. Okay, rows with columns, and then basically I have this quantity, which is simply delta. As we saw here. Okay, this is simply delta, and this delta would essentially set this j and k indices to be equal. Okay, so I could have said that this is j if you like. Okay, this is just j. So you see, this is just a way to show that this is what very similar to dot product, although I have taken a vector and a covector. Okay, if I don't distinguish between the upper and the lower index, which I am free to do because I have this the transform in the same way. Okay, as far as rotations are concerned, and then this is essentially the dot product between two vectors A and B. Okay, so but here I am trying to make a distinction between a vector and a covector, and therefore this is the way to do to define the dot product or the inner product. As why I'm saying this, we'll soon see this distinction is going to be important. Okay, this distinction between the vector and the covector is going to be important, and here, because it doesn't matter whether you're talking about the vector or the covector. Okay, therefore the distinction is irrelevant, and we haven't been distinguishing this. This statement that I have shown here is just the fact that dot product, if I take a dot of two vectors, that is invariant under rotations. I just exhibited in S prime frame, which is the rotated frame, the prime frame. This thing, if I take this dot product, this is the same thing as the prime, the unprimed frame. Okay, so this is denoted by the bar, the prime frame, and the unprimed frame is denoted without anything. So this is the way to see, and I would have just done the same algebraic exercise to show that this is the dot product is invariant under rotations. Okay, that is the same exercise, but here I just wanted to distinguish between the fact, when I define the dot product, I would like to consider one vector and the other covector. Okay, that's what I would like to take. Very good. Now, so this is, if you like, the dot product, okay, which I just defined for you. Now what about tensors? Okay, these are so essentially what are vectors and covectors? These are quantities. They're defined to be quantities which have specific properties under rotations. Okay, they transform in a nice way under rotations. Okay, and these are the essentially these objects, as I'm defining it to you currently, I'm using their properties under rotations to define these objects. Okay, so similarly, I can define tensors in a very similar way. Okay, as being quantities. So a tensor is a quantity with, let's say, n indices, where n can be, like 1, 2. If it is n is 1, then I'm talking about a vector. If n is 2, then I'm talking about, a tensor, a 2 tensor, and so on. Okay, so it can have n indices, and depending on how many indices on top it has, I have to multiply with that lambda matrix that many times, contracting with the right indices here. Okay, so I have to multiply with the lambda matrix as many times as there are number of indices for the tensor. Okay, it can have any number of tensors. So objects like this with more than one indices, they are defined as tensors. A 2 tensor, 3 tensor, depending on 2, 3, 4 indices and so on. Okay, and if it is index on top, then it is like a n0 tensor. Okay, n index on top, 0 index at the bottom. Okay, and if I write the indices below, then I have to multiply with the corresponding matrices. The ones these were the matrices that were there for the derivatives. Okay, so I wrote it this way. Although this matrix and this matrix happens to be identical for rotations, but again I'm trying to make a distinction. So these are the matrices for infinitesimals, how they transform, and these are the matrices as I've written for the derivatives, how they transform. When I'm talking about the lower indices, I'm going to use this kind of matrices, and when I'm talking about the upper indices, I'm going to use this kind of matrices. These two are identical matrices, as we saw. Okay, and therefore there's no point in making a distinction between upper and lower, and therefore it's basically called an n tensor, depending on how many indices it has. Okay, you can write it on top, on bottom. I mean, we have generally written the indices at the bottom, and this kind of justifies why it's perfectly fine to do, because both the infinitesimals and the derivatives, they transform in the same way. Okay, and that is, through them we would like to define the vectors, and how they transform. We'd like to define the vectors and the covectors, and the index on top or index at the bottom. And we don't want to distinguish between them as far as rotations are concerned. We may not distinguish between them. But here, this is the layout. This is the more or less the layout. Okay. Again, we have already seen two objects which transform in this way. Okay. Like in our discussion so far, we have seen the electric quadrupole moment tensor. This is a 2 tensor because it transforms precisely in this way. Okay, it is a 2 tensor. Okay, we have also seen the Maxwell stress tensor. It is also a 2 tensor which transforms precisely this way with two matrices. Two rotation matrices. Okay, so they have 2 indices. So it is a 2 tensor, and because we we need not distinguish between up and bottom. Like lower indices and upper indices. Therefore, we write everything as a lower index and basically call it an n tensor depending on how many indices it has. Okay, as far as rotations are concerned. Okay, so now, so this was the more or less the definition of vector, covector, tensor. Okay, so these vectors and tensors, as far as rotation group is concerned, again, when you do group theory in your next next semester or higher studies, you will see that what we are talking about, these vectors and tensors are essentially so-called representation of the rotation group. Okay, whatever the rotation group is in any dimension that you're talking about. Okay, so these are again, that is a different point of view for vectors and tensors. But as far as you understand this, I think this understanding is enough for not only for now, I mean, this is also the right kind of understanding, understanding vectors and tensors through their properties under rotations, okay, how they transform under this thing. Okay, that is how vectors and tensors are defined. Okay, very good. So now it's time to look at Lorentz transformations and define vectors and tensors in terms of Lorentz transformation in space-time. So till now, we were talking about spatial coordinates only. Okay, so if you like, this I and j coordinates ran over 1, 2, and 3. Okay, only the spatial coordinates. But now it's time to look at space-time and consider, apart from rotations, also Lorentz boost transformations. So Lorentz transformation is a combination of Lorentz boosts and rotations. So we will now look at the boosts and try to see what is going on. Okay, so let's try to look at the boost. Let us perform an identical analysis like we did before. So this was this thing was is clearly the boost transformation between unprimed and primed, and this is the boost transform, the same inverse transformation between primed and unprimed. Okay, that's the relation. Okay, now we can take it again. This prime I'm denoting by bar. Okay, so I'm using this interchangeably. I hope this is all right. Okay, so let's first check how the infinitesimal transforms. So the infinitesimal must transform in this way, with the x bar mu on top and del x mu. So I have to use this expression to find what the infinitesimals are. Okay, so if I use this expression, then this is just identical here. Okay, so also I must say that now I'm using a different index notation. Apart from ijk, I'm using these Greek indices mu, nu, lambda, etc. And these indices run from 0, 1 to 3. Okay, and you can ask me what is 0, and this x0 is basically c times t. Okay, as you can see that if I, this has the dimension of length, if I multiply with c, and this is c times t, and this is my x0. Okay, so if I have that as my x0, and I want to write down, transformations like this, infinitesimal transformations like this, between the infinitesimals in one coordinate compared to the other, then this is the transformation that immediately follows from here. It's just taking a d on top of it, right? These are the expressions that immediately follow. Okay, so now also this one I can also think of as a matrix, because here I have a mu, here I have a nu, and there's a matrix multiplying. This is a column, and this is a column, and this is a 2 cross 2 matrix. And that 2 cross 2 matrix, if I read it off from here, okay, these terms, then I can clearly see that, my 2 cross 2 matrix C times, this thing is basically C times T times gamma. So this is my first entry. Okay, so here I have used, the thing, let me write it here. So this is my x naught, this is my x, this is my x. Okay, this is the way I have used it. Okay, this is x naught, x. Okay, so that's the way I have used this. I have written this matrix, and so this, if I just plug it in here, then I'll get this transformation which I have here. Okay, very good. So, and this can be immediately followed just from this kind of transformation properties. Okay, now what about the derivatives? The derivatives have a different kind of transformation. For the derivatives, I have to use this thing, the unprimed in terms of the primed. Okay, so if I use that and figure out what the derivatives look like, they have this kind of things. You see, there's a crucial difference in sign here, because this is the inverse. So I have to take v2 minus v. So there's a difference in sign, and because of the difference in sign, I see that when I write down, so this thing object also I can write down as a matrix. Okay, this matrix, when I write down lambda tilde, this matrix is different. This matrix is different because it transforms in this way. Okay, so somehow I have missed, let me write it here. So lambda tilde, if I just read it off, okay, this is basically gamma beta. Let me see this. Gamma beta. Okay, I'm just reading off. So this is del x naught. Okay, this is del x naught. This is del x naught, and x naught. This is del x naught bar, and this is del x naught del x, and this is del x x bar, and this is del x naught del x. Okay, so I'm just reading off the coefficients and writing it here as a matrix. Okay, so so this is this is essentially this matrix tilde is essentially this this derivative here. Okay, and as you can see now, it's very clear that this matrix is very different from this matrix out here, because the signs are different and there's no way that the signs will be the same. Okay, so this tilde, that's why a tilde is not equal to, lambda tilde is not equal to lambda. Okay, so the infinitesimals and the derivatives, they transform differently when we are talking about Lorentz boost transformations. They transform in the same way when we talk about rotations, but they transform differently when we talk about boosts. Okay, so therefore we can define a 4 vector. That means a vector now having 4 indices, times and 3 spatial indices. So that's why it's a 4 vector. That's why the name 4. Okay, so a quantity which which has 4 components. Okay, which transforms like the infinitesimals. Okay, with this, this being the matrix, okay, which transforms in this way, that is called a 4 vector. Similarly, a quantity with an index down now, okay, the vector I am denoting with the index up. Now a quantity with an index down which transforms as the derivatives, they are called 4 covectors. So a vector transforms as the infinitesimals of the coordinates, and that and a covector transforms as the derivatives, and these matrices are in general different. As you can see here, there's a sign difference here. I hope the definition of the vector and the covector is clear. That one that transforms as the infinitesimals, and the other one is the one that transforms as the derivatives. Okay, if you like, this is the, you need not talk about infinitesimals or derivatives or as such. Okay, I mean, you can just take this and say that anything that transforms like this is a vector, anything that transforms like this is a covector. That's it. Okay, so and the transformations are different, so the vector and the covector has to be distinguished. So the vectors, I'll write the index on top, that's an upper index, and the covectors, I'll write the index below, that's a lower index. Okay, very good. So I have a vector and a covector. Now let's look at this product here. Okay, again, Einstein convention applied, so there's a sum over mu, and mu goes from, again, 0, 1, 2, 3 in general. I mean, here it just goes over 0 and 1, if I think of as 2 cross 2 matrices. But again, you can put in the other part, you can put in 0, 0, 1, 0, 0, 1 and 0, 0, 0, 1, 0, 0, 1. Because under this transformation, the y and the x, that is, under the boost along x, the y and the z, is not affected. So very good. So this one is the product now, v mu bar, w mu bar, but the indices, they are summed over, and as you will see now, it is always, these sum over indices, we are always going to sum the upper indices with the lower indices. Okay, this is like a mnemonic, you should remember that. That is what gives you nice quantities, as we are going to demonstrate now. Okay, so this, setting equal and doing a sum that we did, previously, that was essentially doing a dot product. This is what is going to replace a dot product. So you can only take a dot product between two, between a vector and a covector. Okay, rather than a vector and a vector, you have to take a vector and a covector and then, do a dot. Only then, as you can see, is that this is Lorentz invariant. Okay, why is it Lorentz invariant? Because the V mu will transform with the lambda matrix, and the W mu will transform with the lambda tilde matrix. And as you can see, as I have written here, this expression, if you see, this mu and mu is summed over. So because mu and mu is summed over, this is nothing but del x lambda del x nu. So this is just a Kronecker delta nu lambda. Only when this nu and lambda are equal, then this derivative is non-zero, and then this delta, kind of enforces these two indices to be equal, nu and nu. So essentially, this thing remains the same as remains invariant, if you like, under a coordinate transformation. This kind of product. Okay, so this kind of product is going to be called the inner product, and so you can check it the matrix way. You can put in the matrices, and you can see that this matrix reduces to the identity matrix. Just remembering that gamma square is nothing but 1 by 1 minus beta square. Okay, just remembering that, you can just derive that these two matrices here. These two matrices essentially multiply and give the identity matrix. Okay. So therefore, this object is invariant. The product between a vector and a covector, and summing over the components, that is invariant under Lorentz boosts. And of course, that will also be invariant under Lorentz under rotations, because the rotation is just a part of it. And for the rotations, it doesn't matter whether you're writing an up or bottom. Okay, so it's really that part would also follow. Okay, as we have seen, for rotations also it is invariant. Okay, so very good. So now, right. So now, so this is like a scalar which does not transform. So we can look at this object, and therefore we can say that every W, okay, which is a covector, takes a vector and maps it to a scalar real number. Because you can take, given a W and given any other vector, you can take and multiply it and sum over the indices, and to get a number which is the scalar number. Okay, so basically I can think of as the covectors as like the set of all maps which takes a vector and maps it to a invariant scalar real number. Okay. So that we can think of that as this. Okay, and similarly we can think of the vectors as being the set of all maps that takes a covector and maps it to a invariant real number. Okay, because this object is invariant. Okay, so this is the thing. I mean, in fact, covectors are sometimes defined that way. That it's a set of these maps. Okay, but anyway, so I mean, I'm defining it in this way. I think it's just. I'm just, I'm not trying to be very mathematically rigorous. I'm just trying to give you the story, the kind of things that you will find it useful if you ever try to do it more rigorously than this. Okay. So this is more like a working knowledge of the stuff. Okay. Rather than trying to be rigorous. So very good. So these were the vectors and the covectors as far as Lorentz boosts were concerned. And then we have 4 tensors. Okay. We have 4 tensors. And the 4 tensors are essentially objects now with, let's say, n upper indices and m lower indices. Of course, I have to now distinguish between the upper and the lower indices because they transform differently. Okay, and corresponding to every upper index, you put in a lambda, and corresponding to every lower index, you put in a lambda tilde. Okay, this is how the infinitesimals transformed, and this is how the derivatives transformed. So, the lower indices transforms like the derivatives, and the upper indices transforms like the infinitesimals. Okay. So, with that, you can define objects which are called tensors, mn tensors. Okay, these are mixed tensored, if you like. You can have both mn and non-zero, then these are called mixed tensors. So they have upper and lower indices, and so the idea is this, that if you have upper and lower indices, then they transform in a particular way, and that is their definition, if you like. Okay, this is their definition. Okay, and this therefore defines tensors. So basically, a vector is basically a 1-0 tensor. A vector is a 1-0 tensor, and a covector is a 0-1 tensor. Okay. Similarly, you can have 2-0 tensors and so on. Okay, but you have to remember now these indices, they run over 4 coordinates. They also have the time part in it. Okay, that you have to remember. Okay, so that's very good. So that's the definition of 4 tensors for you. Okay, and I guess we'll see one 2,0 tensor in this game, okay, very soon in our discussion of electrodynamics. But apart from, this is the energy momentum tensor. But apart from this, we'll not see a lot of tensors in our discussion. Okay. And also, there's also going to be a 0,2 tensor. This is again the field tensor, which is the electric and magnetic fields. Will again, we'll come to that. Let's not rush. So yeah. So therefore, this is the property of transformation. Okay. Vectors, covectors, and tensors defined through their transformation properties. Excellent. Now, let us say, let us come to the concept of the metric. Okay, let us come to the concept of the metric, which is defined over space-time. And this is, as I said, this has got to do with the interval, which is a notion of distance. Okay, so that's why, I guess the name metric, because it is associated to a notion of distance. And so we do it in the following way. So you see, we have this invariant interval again. Okay, the interval was invariant, so we have this invariant interval. And in this invariant interval, what we are doing in this invariant interval, we can take this and think of this as a matrix with mu and nu index and dx mu dx nu. Okay, so these are the infinitesimals. Of course, these are the infinitesimals. So I can take the interval, the infinitesimal interval, and I can write it in terms of define mu nu with this metric. Okay, and this mu nu has the form, as you can see here. It's a +1 minus minus minus, and it's a diagonal matrix with plus minus minus minus, and so this is an object which transforms as a 2 tensor, 0,2 tensor. Okay, as you can see, if this transforms as a 0,2 tensor, then so basically, so therefore, this is going to transform like I'll have 2 lambda tildes here, and there will be 2 lambdas coming from here. Okay, from these 2 dx's, how they transform, and therefore the lambda tilde and the lambda multiplied, as we saw, that gives identity. Therefore, this is going to be invariant under any Lorentz transformation, and therefore this is the interval is going to remain invariant. Okay, so again, just as a thing to quick thing to check, as long as these indices they're contracted. By contracted, I mean they're summed over, they're set equal and summed over. That happens with lower and upper indices. As long as that happens, then I think you can safely say that this object is invariant, because the lower objects transform in a way which gives us the lambda matrix, and the upper objects. The upper object gives us the lambda matrix, and the lower the lambda tilde matrix, and then they would multiply and give us basically they would give us the same, this give us identity. So therefore, it will remain invariant. Okay, that's the idea. So this is a definition for the metric for you. By the way, this kind of space-time, okay. So earlier, when we were talking about Cartesian coordinates in Euclidean spaces, okay. So if you look at the spatial part around us, these are essentially like well approximated by Euclidean spaces, and so essentially, this space-time is clearly not Euclidean, and this has a name. It's called Minkowski space. Okay. So the space-time, as we are describing here, together, space and time together, that is a Minkowski space with this particular metric. And we have again, the overall sign of the metric is a convention, but we have chosen a particular convention. So this is the Minkowski space metric, and we have chosen the analog of this Cartesian coordinates in Minkowski space. Of course, the spatial parts, as you can see, we have chosen Cartesian coordinates, and of course, and this time part also we have included. And these are the analog of what you would call as Cartesian coordinates in Minkowski space-time. Okay, and in that case, the metric is extremely trivial. It just essentially a diagonal bunch of ones and minus ones. Okay, so this, as I said, metric is this 0,2 tensor, so it transforms in that way, and this keeps this object invariant. The interval, it keeps invariant. It ensures that, but we also know that the interval has this form when we are talking about these so-called Cartesian coordinates, and the interval has this form in in the unprimed case, in the primed case as well as in the unprimed case. Okay, the interval has the same form. This we have seen. Now, if we now consider, so both the eta in the primed coordinate is also the same object as in the unprimed coordinate. It's the same eta. Okay, so basically we can write the same eta. Okay, both in the unprimed and the primed, as far as Lorentz transformation are concerned. Okay, as far as that is concerned, we can write the same eta. Okay, as this is again, I'm talking about this interval. Okay, so if I write the same eta down on both sides, then you see, now I can do a transformation on this infinitesimals that gives me this lambda matrices. Okay, that gives me this lambda matrices. So this eta times these two lambda matrices should also be equal to eta, because these infinitesimals can again be arbitrary infinitesimals. So you can compare their coefficients. Okay, comparing coefficients, the eta must satisfy this. Okay, so in some sense you can define the Lorentz transformations as transformations that satisfies this thing equivalently. So we were initially it's the same thing that we discussed, that how Lorentz transformations are these transformations that keeps the interval invariant, and the interval had to be invariant. It follows from the postulates. So this was this is just a fact that is true for the eta. Okay, and you can check in terms of matrix multiplication. You can check that this is valid. Okay, I've checked you for it, verified this expression for it here. Okay, this is a valid expression. Now, if I have this expression, then it immediately follows that if I take two vectors and put a eta and contract it in this way, then this is going to be invariant. Why? Because by definition, the vectors are objects that transforms like the infinitesimals. And therefore, these are the things that generated from the infinitesimals. So, if I do a coordinate, a boost transformation, let's say, then what I'm going to get is this eta times this lambda matrices here. Okay. And if I get those lambda matrices, then eta times those lambda matrices, that is going to give me an eta back. Okay. And that, therefore, this form is going to remain invariant. Okay. So this immediately allows us. So this we conclude as this is like a invariant. It's like a under boosts. Okay. So this object is a invariant, and we call it a scalar. That's what we by scalar we mean with something which does not transform. Okay. So therefore this is a scalar invariant. And now if you stop to think, then this object is a scalar invariant. Okay, so this object, therefore, this is eta times this vector, therefore takes the vector v2 and maps it to a scalar invariant real number. Okay, and therefore this object can be thought of as a covector. Okay, so this is the idea, that I have taken two vectors multiplied by eta, and the property of eta ensured that this was a invariant. And now once that is an invariant, we can think of this combination as a covector, and therefore I can, although I have taken, so this kind of thing, I can always do. So I can think of these things as, as some kind of, like a covector which maps my vector to a scalar invariant real number. So therefore I see that the metric takes my vector and makes it into a covector just by multiplying and contracting or summing over one of the indices. Okay, if I do that, then my metric converts this into a covector, and this also index wise this is true, because if I contract these two indices, then the free index is nu, which is a index at the bottom. So this object also transforms like a covector. That you can check. This is your exercise to verify that this object transforms like a covector. Okay, so now given a covector, okay, let's say we write that a covector is like this, okay, because I can take a vector and map it to a covector. So basically, let me take a covector and write it in this form, that I have taken some vector v and convert it into a covector through this. Okay, so if I do that, then to this covector I can always multiply the inverse matrix. Okay, this inverse matrix I'm denoting with the matrix on indices on top for reasons as you will see right now. So if I take the inverse matrix and you multiply these two matrices, because this is the inverse of each of this thing, okay, that is going to give me an identity, and then I'm going to get back this vector v. Okay, I'm going to get back this vector v. So basically this inverse metric, that object, so you can work out, because this is the eta, and the eta inverse, if you find the inverse of it, it's going to be the same matrix. Okay, it's going to be the same diagonal matrix 1 minus 1 minus 1. It's very clear. If you take the inverse of it, it remains the same. Okay, this one is its own inverse. Okay, so this eta inverse is the same matrix, but because it's the inverse, I'm going to denote it with the indices on top, and that if I multiply with this form of this covector, I'm going to get back the vector, okay, which I multiplied the eta and converted into a covector, that I'll get back if I use the metric and inverse metric and multiply it in this way. Okay, please note that these indices are contracted. Okay, it's the same indices. Okay, because I'm doing matrix multiplication. So basically, and you can also check that this object transforms as a 2, 0 tensor. The metric transforms as a 0, 2 tensor, and this object, the inverse, transforms as a 2, 0 tensor. Okay, so this kind of thing follows from this fact, from the properties of this eta. Okay, you can check that. Okay, so so this object, therefore, the inverse metric maps a covector to a vector. Okay, so a vector, if you like, is mapped to a covector by eta lower, and a covector is mapped to a vector by eta upper. Okay, essentially they are the, as far as this Minkowski space and this metric is concerned, essentially they are the same. Okay, but I'm just making a distinction between the metric and the metric inverse, and so the metric maps vectors to covectors, and the inverse metric maps covectors to vectors, if you like. Okay, so so basically the metric, therefore, can be used to raise and lower indices. Okay, given a vector, you can find a covector by multiplying with the metric. Okay, and similarly vice versa. So you can use to raise and lower indices with the metric, and therefore we have to, and because the metric has this special signs, we just have to be careful with the signs as far as upper and lower indices are concerned. Okay, otherwise, it's so given a vector, I can always find a corresponding covector, and given a covector, I can always find a corresponding vector. Okay, by using the metric. Okay. So that is what I want you to appreciate, and that's that's a matter of sign. Okay, the distinction is just a matter of sign for the spatial components. Okay, that's the distinction. Okay, very good. Now, as I mentioned before, okay, given two vectors, I can construct this object, which is a scalar invariant. I can take the metric and multiply them. It's a scalar invariant, and this object, depending, this object can have various signs. Okay, so if I take a, if I am given a vector, I can construct its corresponding covector and then take a, like a inner product with this. This is like an inner product. Okay, and depending on this object, the sign of this object, I can classify vectors to be time-like, space-like, and light-like, like we did for the interval. Okay, so I can take a vector and find this object. So this is a scalar real number. If this is greater than 0, then I call it a time-like vector. If this is less than 0, I call it a space-like vector and a light-like vector. So the terminology that is used for the interval is also, can be used for the vectors. Okay, the one that is a light-like vector is often called a null vector. Okay, because if you like, its norm vanishes. Okay, so if you like, this is the generalization of the idea of dot product with 4 vectors. Okay, so you can't just take them and multiply them. This is one thing that you can appreciate, that you can't just take them and multiply them. You have to put in the signs, corresponding signs. Okay, so if I give you, just to make this point, this is an important point. So if I give you a vector v mu, okay, which is, let's say, v0, v1, v2, v3. Okay, if I did a naive multiplication like v mu, okay, this was the kind of dot product that you did, right? You just took the components in Cartesian components and you multiplied them, right? But if I did that, then this object is going to be v0 square plus v1 square plus v2 square plus v3 square. Okay, it turns out that this object is not invariant under Boost transformations. What you have to do instead is consider the quantity which is v mu eta mu nu v nu. Okay, contraction. And this, if you evaluate, you will find that this is equal to v0 square minus v1 square minus v2 square minus v3 square. And this quantity is the quantity that is invariant under Lorentz transformation. Okay, so this is the difference, that here, while taking the dot product, we just multiplied the components and added it. But here we can also multiply the components, but the spatial components we have to consider a sign because of the metric here. Okay, this is the working knowledge that I want you to appreciate. Okay, so very nice. Now, so now let us consider example, because there was a lot of abstract discussion so far. So let's consider an exact example. Let's consider the relativistic 4 velocity of a particle. Okay, so how do I do that? How do I construct the 4 velocity of a particle? So as we saw, there was this proper time. This was the proper time. This is the interval divided by c for a particle, let's say. Okay, a particle is there, and proper time means what? Okay, this infinitesimal interval is basically the time measured by a clock, which is sitting on top of the particle. Okay, it's the time of the particle. Okay, so time in the rest frame of the particle, that's like proper time. And that is definitely the interval between the 2 points. Let's say the particle, existed at some point, and, in this thing, let's say making some motion. Okay, so in the proper time, okay, let's say, the particle is this thing in some frame, it's making some motion. So the particle is going from here to here. So in its own frame, it is like stationary at the same point. And in the moving frame, it has like moved from one point to another. Okay, so therefore the interval between the two events, that is ds. Okay, and the proper time is simply ds by c. Okay, so because it is ds by c, and we know that in the moving frame, this time, this we have seen a while ago, that this time, this infinitesimal time interval in the frame where it is moving, the proper time is expressed as t by gamma, and this gamma is root over 1 minus beta squared. This beta squared is v by c. v square by c square. Okay, that's beta square for you. Okay, so this is the proper time. Now, the forward velocity v mu is basically d coordinate x mu d proper time. Okay, so this proper time is basically, if you like, it is often referred to as an invariant. Okay, because it is directly equal to the interval, which is invariant under transformation. So proper time is the time in a particular frame of reference. Okay, so saying it an invariant doesn't make any sense, because it is defined as the time in a particular coordinate. Okay, but sometimes people say that proper time is invariant in the sense that proper time is precisely equal to the interval, which is invariant under boosts. So therefore proper time is invariant. That is the sense in which people use the idea that proper time is a invariant. So basically, I take the coordinates, infinitesimal coordinates, and divide it by the proper time, and take the limit proper time goes to this thing. So this defines for me a derivative, and this derivative is basically the forward velocity. Okay. Now, because this is related to the time coordinate, the time in the moving frame, that moving frame, it is related by this factor of gamma, where this gamma has the beta, which is the beta of the moving, this is the velocity of the particle, if you like. Okay, so basically this gamma has the velocity, but now in the frame where it is moving, okay, this dx, by the way, is in the unprimed, like in the moving, in the frame where it is moving. Okay, so then dx by dt is simply, so dx mu, x mu is what? X naught. So dx naught dt is simply equal to c, because x naught is basically c times t, right? So this first component is just c, and the second component is just dxi dt, and this is nothing but the velocity, right? I again denotes 1, 2, 3. Okay, so this is, if you like, the forward velocity has a time component which is gamma times c, and a space component which is gamma times v. Okay, so as you have seen before, that the addition of velocities, from the addition of velocities, you have seen that velocities doesn't transform in a nice way. Okay, but if you multiply it by gamma, where gamma is the 1 by root over 1 minus beta square, where this beta is the same velocity. Okay, so if you multiply it by gamma, this object transforms nicely like the components of a 4 vector. Okay, which is much nicer if you just compare to how the velocity is transformed in general. Okay, so this gamma factor is somehow magical in some sense. Okay, so but the forward velocity of the particle is given by this. So in the non-relativistic limit, as you can see, in the non-relativistic limit where the gamma, that tends to 1, in that case, this is nothing but the velocity, and it has a fourth component, which is the time component, and that is given by c, essentially. Okay, so this is the definition of the forward velocity, if you like. And as you can see, if I take the forward velocity and what did I do here? What I mean is, if I convert the corresponding, convert it to the corresponding covector, forward covector. So the forward velocity vector is given by this object, gamma c times v, gamma c comma v. So this is time, 0 component, these are the 1, 2, 3 components. Okay, that's why the vector sign. Okay, so this is the expression for the vector. Now what about the covector? The covector has to be multiplied by the eta to get to the covector. Okay, and the multiplication by eta essentially introduces a sign in the spatial coordinates. Okay, that's all it does. So this v becomes minus v for the covector. Okay, now if we take the vector and covector dot, then this is the inner product, or this, if you like, this is the norm of the forward velocity vector. Okay, if this is the norm of the forward velocity vector, then this is given by, so this is component by component. Now you can take them and add them. Okay, so again, this is something which is very important. Okay, let me highlight it. Here I have said that you need to do this. Okay, but if you had, if I told you that my v mu was this, and so let me use this thing. So my v mu was this, and then my V mu lower is basically nothing but, if I denote that as V naught, V1, I don't have space. So, yeah. If the lower one I denote as V mu lower, this is like V naught, V1, V2, V3, okay, then I can write down V mu, okay, that is the same thing as this, by the way, okay, that is the same thing as, this is the same thing as this, because, you know, I can use the eta to get these components, okay, and if it is like written like this, then I can simply multiply. Then it's like, you know, V naught times V naught plus V1 times V1. You know, the difference is between this one and this one is that, you know, the V1 upper and the V1 lower, they differ by a sign. Okay, plus V1, V2, V2, okay, plus V3, V3. I hope this is clear. Okay, and this, once you use the eta to lower it, then this object becomes equivalent to this object here. Okay, so I hope this thing was clear, and therefore if we now compute this V mu, okay, if we now compute this V mu, then we get, so the gamma square will come here, C square, and then you can just multiply them. If you write upper and lower, you can just directly multiply them. Then you get a minus V square. Okay, if you get a minus V square, you can take the C common, and then you get 1 minus V square by C square, and this gamma is 1 by 1, gamma square is 1 by 1, 1 minus V square, 1 minus V square by C square. Okay, there is a square here. Okay, so that cancels and you get a C square. You just take the C square out and you will see that the algebra works out. And this is greater than 0 because C square, you know, it's a positive thing. So it's greater than 0. Because this is a greater than 0, therefore this 4 velocity vector is a time-like vector. Okay, therefore this is a time-like vector. Okay, very good. So this is just an example. Similarly, you can define acceleration. Now you take the 4 velocity and then you differentiate with respect to proper time again. Okay, dv d tau. Okay, this again defines for you an acceleration, which is this is a 4 acceleration vector, if you like. Okay, so very good. Yeah. So if you like, if I write it out, then this one will have the gamma factor, and then there's a gamma factor here, and then there is, you know, this is the 4 vector. You know, this is the 4 velocity vector, right? So now you see the derivative can not only hit the velocity here if it is time dependent, it can also act on the velocity present in the gamma. Okay, that gives you additional terms essentially. Okay, so the 4 acceleration is a very, very complicated quantity. Okay, because of this gamma factor. Okay, of course there's an outside gamma factor, but there's also a gamma factor inside the derivative which needs to be taken into account, and that makes it slightly complicated quantity to deal with. Okay, very good. So so let's start with this fact. Okay, there's one feature about the acceleration that is important. So if we, the 4 acceleration, yeah. So if we take the 4 velocity and you know, take the inner product between 2 4 velocity, you know, like the vector and the co-vector, if we dot, then we get C square. Okay, this we have seen here. Okay, we've seen here that we get C square. Now you can take a derivative with respect to proper time d tau. So if you take a derivative, then this is going to give me a 2 times V mu. You know, this is 4 acceleration. And that on this side, the derivative with respect to proper time, that is going to give me 0 because speed of light, you know, that's always, you know, that's just a constant. So that's 0. If that's 0, then I would conclude that the inner product between 4 velocity and 4 acceleration, that is equal to 0. So in the 4 vector sense, velocity and acceleration, the 4 velocity and 4 acceleration, you know, these are mutually perpendicular in this sense. Okay, that their inner product vanishes. Okay, so in this sense, they are mutually orthogonal. Okay, so very good. That's something. Okay, so before we switch to, you know, a little bit of discussion about dynamics, I have a few things to say about, you know, these are just some brief remarks about 4 vector calculus, if you like. You know, so you remember we started this course with vector calculus, okay, talking about gradients, divergences, curls, and whatnot, okay, about vectors. But now we have a new new quantity in the game. These are 4 vectors. These are like 4 components. Okay, so similarly, you can define a vector calculus for these 4 vectors. Okay, so which I'm calling 4 vector calculus for the lack of a better word. Okay, so I'm so let's look at 4 vector calculus. So how do you define? This is like 4 meaning in 4 dimensions, in space-time dimensions. Okay, space-time taken into account. So this is the thing. One of the main things about special relativity is like it puts time in the same footing as space, right? That's the main thing about special relativity. That you can think of the Lorentz transformation, which is like a rotation of coordinates. Okay, it's not only a rotation in the spatial coordinates, but it's also a rotation involving space and time. That's the boost for you. The boost mix up the space and time, and it's almost like a rotation. The sine is replaced by sinh, and the cosh is replaced by cosh. Okay, the hyperbolic function. So it's almost like a rotation. So in many good sense, this is like a Lorentz transformation is like a rotation. Okay, so if this is like a rotation, then essentially most of the features that we saw for vectors and tensors in 3 dimensions, that kind of carries over to 4 dimension as well. Okay, so we have to treat time in the same footing as space, and we have to develop everything, and then only then we can be consistent with special relativity. Okay, that's the bottom line of the message. Very good. Now we can take this. First we can define the simplest quantity, which is basically the 4 gradient. So if we have a scalar, okay, let's say a scalar field. Now this is a scalar field over space-time. So we have to remember that this object is a function of x, y. It's not only a scalar field over space, but it's also a scalar field over time. And this time, I'll just put a c here, just for fun. Okay, make this the x0 coordinate essentially. Okay, so this is a function of space and time. Okay, so this is a scalar over by scalar I mean that it does not transform under a Lorentz transformation. That is a scalar. Now if I take that, and if I take that, and if I now put in a derivative like this, you remember we had while taking gradient, we had defined it as del I phi. You remember, for the 4-dimensional case. Okay, so this is here we are doing the same thing. It's just that I'm reserving the symbol nabla for the 3 divergence. Okay, and here del I phi, this I can directly write as del mu phi, where I have this object now has 4 components. Okay, so this object is a 4 vector with 4 components. The first one is the derivative with respect to x0, and the second and the 2, 3, 4 components. These are essentially the 3 gradient. Okay, that's the gradient of phi. Okay, that is the definition of the 4 gradient. Okay, so this transforms as a 4 covector. I should emphasize that. So this transforms as a 4 covector. Okay, so you can check whether it transforms as a 4 covector or not. Okay, of course, here we actually have a derivative, so it better transform like a derivative. Okay, so it transforms like a covector. Okay, very good. Now let's now consider the vector. I'm so sorry, the corresponding vector. Yeah, I just messed this up. Let's now consider the corresponding vector with the index raised. So if I have the index raised, I can do that with a metric. Essentially, this is nothing but the inverse metric. Okay, so if I do that, work it out, you will just get this object with a minus sign here. Okay, so that's what you get. And now we can take the vector and the covector, and so the covector and the vector here, and perform a dot between them to form a scalar invariant. So we can take this object and we can write down something like del mu phi, del mu phi. The indices just keep track of that, and that would be this object. This object therefore will be a scalar invariant, something which is invariant under Lorentz transformation. Obviously, this tells us it is going to be invariant under rotation, and this form, this particular form, ensures that it is invariant under rotations, invariant under boosts as well. Okay, so right now we can take the 4 divergence. Now we can take the 4 divergence, which is this. We can take the 4 divergence. So let us say that we have a vector field over space-time again. Okay, A mu is the vector field over space-time, and then if we just do a del mu A mu, this is going to be a scalar. You can check again that this is going to be a scalar, and this object is called the 4 divergence of the vector of the 4 vector field A mu. Okay, right. So so this is the definition. Okay, it's just a generalization of the idea of the 3 divergence. Okay, so now you can ask what is the box operator. Okay, so the box operator, this is the operator which is del mu. Okay, so this box operator is the del mu operator, where there's a mu and mu. This is a lower and a upper, and that's contracted. Okay, this operator is basically operator with a time derivative and space derivative, and if we raise it, then it's a time derivative and a minus sign here, and then if we contract it, or if we take and put a sum, that gives me the box operator, and this is the time derivative square minus this thing. Remember that this is x naught. So basically what I mean by x naught, this thing, I mean that this is del c square, del square, del c square, t square. Okay, that's what I mean. Okay, so this is the, this is what I mean by del x naught here. Okay, so basically this combination is the combination that appeared in the wave equation, if you remember, right? Okay, this is the combination that appeared in the wave equation. What about curl? Okay, this curl is slightly complicated, more complicated than it was in the 4 dimensions. Okay, so this curl, if you like, following the fact that if we're in 4 dimensions, then if we look at the components of the curl, then if you remember, we can write one of the components as something like del a, the z component, del x a y minus del y a z a x, like this. Okay, so following that fact, okay, we can define the curl in this way, but now it has 2 indices. Okay, in the 3 dimension, we had a Levi-Civita tensor with which we can write it. We could have, we wrote it very compactly as a vector. Okay, but here in this case, the Levi-Civita tensor, or sorry, the Levi-Civita symbol, that would have 4 components. Okay, instead of, because this is 4 dimensions, so that has 4 components. Okay, naturally. Okay, and because of that fact, we cannot really take this and make it into a 1 index, reduce it to a single index. We can, if we like, we can contract, put in an epsilon here. If we like, we could put in an epsilon here. Okay, epsilon mu nu sigma lambda, but then sigma lambda, this will again have 2 indices. Okay, so in 4 dimensions, this curl object, okay, cannot be written simply in terms of, let's say, a vector. Okay, in fact, this is, as written, this, as you will see, this has a nice transformation property, and it transforms as a 0,2 tensor. Okay, it has a nice transformation property, but it transforms as a 0,2 tensor. So the curl is a 0,2 tensor. Okay, in four dimensions. Okay, so we also have the Levi-Civita here, that is there, but it has 4 components, and the definition is again the same. If it is 0, 1, 2, 3, then it is equal to 1, and all symmetric permutations, it is +1, and all antisymmetric permutations. So 1, 0, 2, 3, that's going to be -1. Okay, so it's like a completely antisymmetric symbol. Okay, so it's the same thing, and again here you can do a 4x4 determinant to with the deltas to tell you what this epsilon is. I mean, there's a sign here, of course, because one of the this thing, you have to be careful about, because about up and lower indices, that kind of being in the sign, because I've written it in the way, up and lower. But this one delta, this is like that. If whenever mu lambda when it is equal to 1, whenever mu is equal to lambda, it's that just defined that way. Okay, otherwise it's 0. Okay, so it's defined in the usual way. So delta mu alpha is equal to 1 if mu equals to alpha, and equal to 0 if mu is not equal to alpha. Okay, it's the usual definition for the delta. Okay, although I have written it, up and up index and down index. Okay, so right. So now, right. So you can take and perform contractions now. Here you can set the indices equal, and then I have not written when one index is equal. Okay. Right. So I have written the one that's like 2 indices, they are equal. Okay. Then you will get this. You can just verify by contracting from here. Okay. So, and when 3 indices are equal, okay, then you get this. And when 4 indices are equal, you get minus 24. Okay. So because this is, the dimension is different, then therefore, these numbers are different. Okay. So this you can just check and verify. Very good. So this is the Levi-Civita in 4 dimensions. We'll just need this, one very, we may need this a little bit. But again, we are not going to do too many manipulations with this for Levi-Civita. So this, this kind of construct. But again, I mean, this is, it may be nice if you can get familiar with it. But too much, like the rigorous manipulations that we did with the 3-dimensional epsilon. That will not involve so many, at least for this course, it will not involve so many manipulations with the 4-dimensional Levi-Civita. So so now the last 2 things is, of course, you can define a 4-volume element. So this is a 4-volume element, okay, and a 4-surface element. Okay, so the 4-volume element is basically, of course, in Cartesian coordinates, you have the space part, and then there is time. Okay, c dt. Okay, that part is there. Okay, so that is there. Okay, so basically, right. Basically, you have this. This is the 4 space-time volume element. Okay, that's the definition of it, if you like. And the surface element also, you can define it in many ways, but essentially, again, let me say that so this is like the surface. Okay, it's a codimension 1 surface, means this is a 3-dimensional quantity. Okay, a surface in 4 dimensions is like a 3-dimensional quantity. So this ds is like a 3-dimensional volume, and this n mu vector, the direction, again, is the direction perpendicular to the volume, because this is 4 dimensions. So a 3-dimension volume can also have 1 perpendicular direction, right? Because we are talking about 4 dimension space time. Okay, so if you like, this is a vector which is perpendicular to this volume. Okay, perpendicular in the sense of there are that is a little bit, it's a little bit dicey, but because there can be null vectors, etc., etc. Okay, but let's assume that we are talking about let's say a space-like surface. Okay, and if this is a space-like surface, then this is like a time-like vector. Okay, so that's what I mean. Okay, so so it's like a spatial. What I mean is, this is a spatial volume, then this is like a time-like vector. Okay, so right. But again, this is you can think of it as the same analogy with the same analogy as you think of surfaces and perpendicular things to the surface. Okay, and then this is the surface element. I mean, there's a formal way to define it in terms of determinants and infinitesimals and determinants, but like you define ordinary surfaces, so you can define it in that way. Okay, so so the reason why I mentioned these 2, volume element and surface element, is that there is a corresponding divergence theorem even in 4 dimensions. Okay, So if you take a quantity which is the divergence, the 4 divergence of a vector, and you integrate it over a 4-dimensional space-time. Okay, this is a 4-dimensional volume element, and this is a 4-dimensional volume, omega. Okay, then you get the surface vector. Okay, this surface vector contracted with the vector whose divergence is here, and this surface is essentially the boundary surface of this 4 volume. So this is like a 3-dimensional object, this is like a 4-dimensional object, and this is like the boundary of this 4-dimensional volume. Just like a 2-dimensional surface is the boundary of a 3-dimensional surface, therefore a 3-dimensional surface is a boundary of a 4-dimensional volume. Okay, and so this is a boundary quantity, and so basically again it's the same thing. A total derivative, if I have a total derivative, then and if I integrate it over space-time, then I get a boundary quantity. Okay, a total derivative always gives a boundary integral. Okay, so this kind of divergence theorem is also valid for 4-dimensional divergences. Okay, so so this is also, you can prove it along the same line as you prove the 3-dimensional divergence, and right. So this is what this is what is enough, at least for this purpose of this course, and right. I mean, again, if we require anything more than this, then we'll I'll tell you about it when we require it. Okay. So yeah, I mean, these little bits, this divergence theorem, etc., will be very useful when we particularly, for instance, look at the Lagrangian and try to derive the equation of motion of electrodynamics or the Maxwell's equation out of a Lagrangian formulation. That in that case, these kind of things are going to be useful. So good. Now, before I end this this video, let me do a quick discussion of the relativistic free particle, and discuss how the dynamics of the relativistic free particle can be derived out of a variation principle starting from an action. So in classical mechanics, you have learnt about actions, and that just to remind you, that the action of a free particle, okay, that is given by the kinetic energy. So you say that this is dt times the the Lagrangian for the free particle. This is given by kinetic energy half m x dot square. Okay, so this is what it is, and that the variation of this, setting that to 0, gives you the equation of motion for the particle, for the free particle, which is again m x double dot is equal to 0. Okay, this is mass times acceleration is equal to 0. So this follows for the free non-relativistic particle. Okay, so this is non-relativistic. Okay, so this is the non-relativistic particle, and right. So this this is just to remind you. But that exercise we are now going to do for a relativistic particle, and we'll see that there's this thing. So you see, the problem with relativistic particle is that this object, we could have done the same thing, but you see this object that I've written here, this is not relativistically invariant. So if you go to a different frame and if you define energy in this way, that this is the kinetic energy or this is the Lagrangian, then this is not going to be because this is a free particle. That's why there's no potential term. That's what I mean by a free particle, that it doesn't undergo any there's no force acting on it. If there's no force acting on it, there's no potential in the Lagrangian. Okay, and then it's entirely given by the kinetic energy. Okay, this is the most simplest thing. And then this object is therefore you can take it and do the variation principle, thinking of s as a functional of this x of t, and that will give you this equation of motion. Right. Now we want to do this in a way which is relativistically invariant. At least the action should be relativistically invariant for a relativistic free particle, right? So so that's what we want. Okay. And the one quantity that is, if you like, invariant for a relativistic particle is its proper time, in the same sense that I mentioned before. So the proper time is directly equal to the interval, and that interval is relativistically invariant. So in this sense, proper time, if I write the action as an integral of the proper time of the particle, okay, then that is relativistically invariant. Okay, and as you will see that this is the right description which reduces to this non-relativistic setup. Okay, so so this is the point. Okay, this is the point that the action has this. The action has this this form that it's proportional to the integral of the proper time. Okay, and the point is that you can study the particle from a different frame where it's moving around, right? But then it has a time of its own, and you take that time and you integrate it, and then we get this this free particle action. Okay, but there can be a proportionality constant alpha, and we'll try to determine alpha. We'll determine alpha from the fact that this action in the non-relativistic limit must reduce to this thing. Okay, this description. Okay, so that we will that's the thing that we will do. Okay, so this action, if I take this action and so there are some properties that I have listed here. So of course this is invariant under Lorentz transformation. This sign here, this minus sign I have put in, this ensures that the action has a minima rather than a maxima. Okay, because we are talking about proper time here. And right, so right, and this right. So this is this thing, and then the proportionality constant I told you would be determined by from the non-relativistic limit, and so the equation of motion, which is this kind of equation of motion, the relativistic equation of motion, that can be derived by varying this action as well. Okay, we'll let's just quickly go through that, and in the process also make some very important remark about the energy and momentum of relativistic particles. So let's say this is our starting point, and if this is our starting point, then first let us determine what this alpha should be. Okay, let's do that. And so if I write it out, the proper time in terms of time dt, I can write it out in this way. Okay, I can write it out in this way. This is basically the gamma factor, this 1 over gamma factor, that comes here. Okay, this we've seen before again when we discussed proper time. So therefore, this is the expression for in a frame where the particle is moving around. Again, as I said, the velocity you can also think of as a function of time. Okay, so now in this expression at least you can think of it as a function. Now, of course, for the free particle, we'll see that of course, it cannot accelerate, for instance, but yeah, we'll see. What are the features. But that is like a solution to the equation of motion, not a priori. Okay, here we're just writing down Lagrangian. So, the Lagrangian here, V is basically x dot, and this x of t is basically the degree of freedom for which we're writing down the Lagrangian. Okay, and this is the Lagrangian. Very good. Now, so if we take this Lagrangian for a free particle, and if we, so this is the Lagrangian, and if we are in the non-relativistic limit, then we can expand, this V by C is small, and we can expand, and the first term that comes is this half factor comes here, right? And then there are higher order terms. And in the strict non-relativistic limit, where you can ignore these higher order terms, then this first term, you see, it has the form V square by 2, and then there's alpha and C square. Okay, and this, as you know, that in the non-relativistic limit must be the kinetic energy. That's what I just mentioned. And if this is the kinetic energy, then the V square cancels from both sides, and you can determine alpha as m times C square. Okay, so alpha is just m times C square. Okay, so that in the non-relativistic limit, this Lagrangian reduces to that of kinetic energy. Okay, it reduces to kinetic energy. Of course, there's this constant piece, But as you know, there's a constant in the Lagrangian does not affect the equation of motion. Okay. So as far as the constant is concerned, in the non-relativistic limit, we can just forget about, because there is a constant in the Lagrangian, right? So this doesn't affect the equation of motion in any way. So therefore, the non-relativistic equation of motion and the non-relativistic dynamics, Newton's laws, that just comes around if I just take this Lagrangian and expand it and keep the first term. That's it. Okay. So that so that it gives the right thing. For that we have to set alpha equal to the mass of the particle. Okay, essentially. Okay, so this is like mc square. Alpha is mc square, so I'm writing it as mc square. This is the Lagrangian. This is the action. Okay, so this we now have the complete action and the Lagrangian of the relativistic free particle, which has the property that it is Lorentz invariant, and it reduces to kinetic energy. The Lagrangian reduces to kinetic energy in the non-relativistic limit, in the small v limit. Okay, that we just checked. Okay, so this is fine then. It kind of agrees with our expectations. Now, if this is the Lagrangian, and if as I said, x as a function of t, this is the degree of freedom, then I can find out what is the conjugate momentum corresponding to the degree of freedom. This is called the momentum. Okay, let's call it momentum. And because so I can think of this particle as all the coordinates. This is like a coordinate as a function of t. And therefore, I can take the Lagrangian and differentiate with the velocity. Okay, so you differentiate with respect to x dot. Okay, that you do to find the conjugate momentum. This again you remember from your classical mechanics, Lagrangian dynamics. Okay, this gives you the conjugate momentum, and this, if you do the differentiation, then you find that this is m times v divided by this factor 1 minus beta square to the half, which is nothing but this gamma factor. So the momentum conjugate to this degree of freedom, that comes out to be gamma times m times v. Okay, so you see, now if you know that momentum is this, then if you now try to find d momentum dt, dp dt, okay, as you know that this is a very important quantity. Okay, so in Newtonian dynamics, so if you try to calculate dp dt, then dp dt is not very simple, because the time derivative hits the velocity in the gammas. Okay, it hits this velocity as well, but it also hits the velocity in the gammas. Okay, now m is always a constant. It's the mass of the particle, and this is what I'll call the mass of the particle. And from this point of view of this Lagrangian, this is just a Lagrangian parameter. It's just a parameter in the Lagrangian or the action. Okay, it's just a constant number. Okay, that's the mass. Okay, so m is always going to be some constant number, but this gamma has a v in it, and this v, this v here. So the time derivative can in general act here as well as here. Okay, so you can make two simplifying assumptions, that if you say that the velocity changes only in the direction and not in magnitude, then this gamma contains the magnitude. In that case, it will not act on the gamma and act on the velocity directly. Okay, so this is the case where if the velocity is changing only in direction, not in magnitude. On the other hand, if it changes in magnitude and not in direction, then basically the v hat, that derivative is going to be equal to 0. But the dv squared dt, this thing is not going to be 0. Okay, so if you just keep track, then there will be two terms, one which is acting on the magnitude of this velocity here for this term, and then there will be another derivative which is acting on the gamma here. So if you just work it out, it comes out to be this expression here. Okay, so right, sorry, in the final step I think I made an error. So this is just dv dt, magnitude, differentiation of magnitude, v. Okay, so this is this is just to show you that how complicated it can get to find dp dt in the relativistic case, because in the relativistic case, what is momentum is simply given by this this object here, gamma mv. Okay, it's not m times v, but it's gamma mv. Okay, and the gamma contains the velocity in it. Okay, the same velocity that is here. Okay, that is there in the gamma. Right. So basically, that was your momentum for you. Now you can ask, what is the energy or the Hamiltonian? You know what is the energy of the Hamiltonian? You just take this. You can define it in the following way. You can take the momentum dot x dot, this object, minus Lagrangian. That's your definition of Hamiltonian. And if you do that, it's gamma m times v square. Okay. And the Lagrangian is basically 1 by gamma mc square. Okay. Mc square was this alpha that got determined. Okay. And there was a minus sign in the Lagrangian that, you have a plus sign here. Okay. So very good. So now you take this and simplify this. Simplify the algebra from the fact, use the fact that gamma 1 over gamma square is 1 minus v square by c square, and this thing cancels here, and that gives you, there's a nice cancellation, and then energy becomes gamma mc square. Okay. So you see, momentum is gamma mv and energy is gamma mc square. Okay. And this reason, this is all, that's all there is to it. Okay. And because of these expressions, sometimes what people do is, people say that, well, I'm going to define a new mass which is gamma times m. Okay. M was this scalar parameter in the Lagrangian. It was just a number, it's like 1, 2, 3, 4. Okay. But then if you multiply it by gamma, then it has some very, complicated transformation properties. Okay. Because the gammas would transform because velocities transform, right? So sometimes people tend to define this m as a rest mass and then gamma time m as the mass. And that is the reason why you have in the formula for Einstein's energy, they just write capital MC square instead of gamma MC square, where it is understood that this m is basically gamma times something called m naught, which is the rest mass. Okay. But I'm not going to introduce this complication. It's not required to define, a mass in a frame, like that. Okay. Because anyway, this is not a nice quantity. It doesn't appear anywhere. All I have is just one mass, and that is the rest mass. And wherever the gammas will appear, I'll keep them explicitly and work with them. That is the best policy. Okay, that is the best policy. Now, so that's just a comment. And now with energy and momentum defined in this way, we come to the main, a very important relationship between energy and momentum. Okay, and that you can see that you can derive by just, so this is the energy and momentum of a free particle. And if you just square the momentum, then you get gamma square m square v square. And if you square the energy, you have gamma square m square c to the 4, because, energy was gamma square m square c square. Gamma mc square. Okay, that's why you have a c to the power 4 here. Right. So now, if you divide energy by c square, then you have gamma square m square c square. And then if you add to it plus gamma m v square minus gamma square m square v square, this is this thing, right? Okay, so you are adding and subtracting this p square. Okay, so this object I'm writing as p square here directly. But now these two objects, I can take the gamma square m square outside and c square outside. Then it becomes 1 minus v square by c square. This cancels with the gamma square, right? And then it becomes p square plus m square times c square. This is just a tidy algebra. Okay, so basically energy square is given by the mod of momentum square c square plus m square c to the 4. This is a very important relationship which plays a very important role in all of our relativistic dynamics of particles, etc. Okay, and this is the relationship between energy, momentum, and mass, rest mass, if you like. Okay, so this is something which is there. The interesting thing is that although we have been talking about massive particles here, okay, there is a discussion of massless particles that you can also do. Okay, you might think that if I set mass to 0, then the Lagrangian would vanish, right? If I talk about a massless particle, then the Lagrangian would vanish. Well, but there is a way to write down the Lagrangian even if the mass is 0. Okay, but again, I'm trying to avoid that discussion there. But this energy momentum relationship, is valid even for a massless particle. Okay, it's valid even for a massless particle. And if I set the mass to 0, or let's say, the mass is so small that, it can be ignored with respect to the momentum. Okay, then in that case, I can write down, I can see that the energy divided by c is the momentum. Okay, so a massless particle can also have momentum just by the virtue of the fact that it has energy. Okay, so basically, this is a very interesting thing. And as you know, that we have encountered such a thing where, there's no mass or massive particle as such, or, we've seen the electromagnetic fields, they have momentum and energy. Okay. And so basically when you do the quantum theory of the electromagnetic fields, or let's say the electromagnetic light waves, okay, they have momentum and energy, we've seen that. So when you do the quantum theory, the quanta of light, the photon, that is a massless particle. And but although it's a massless particle, in the quantum sense of the word, it's a massless relativistic particle. And therefore, it has momentum and energy, and its momentum and energy is related in this way. Okay, its momentum is basically its energy divided by c. Okay, that just comes out of this kind of very simplistic analysis that we just did here as well. Okay, and as you can see, if I draw an analogy with a massive particle, so for a massive particle, the magnitude of momentum. Okay, so of course it can also have the direction of velocity, but the magnitude of momentum is gamma mv, where v is the magnitude of velocity. Okay, so this is the thing, and then the energy is gamma mc squared. So if I write, I can eliminate, gamma m in terms of the energy and write the p as energy times velocity by c squared, the magnitude I'm talking about. Okay, so if I compare this expression with this expression here for a massless particle, then I would conclude that as if the v of the massless particle is c. That must be the case. Okay, so the massless particles must travel at the speed of light. Okay, and that is kind of, if you like, it's a kind of constraint that follows from relativity. Okay, so this is a very interesting thing. And yeah, I mean, one can perhaps do this more rigorously, but I mean, of course, one can do this more rigorously. But this is a very sleek way to see that massless particles must travel at the speed of light. So of course, the light quanta, which are massless particles, they actually travel at the speed of light. That's a reality. Okay. So yeah, I mean, the photons travel at the speed of light. Okay. So that just, simply comes out from this simplistic considerations. Okay. Very good. And now the final step. Okay, that was like energy, momentum, the Lagrangian, that was there. But now the last step, which is basically what is the equation of motion then? Okay, I'm writing down an action. Can I do a variation principle on the action and derive the equation of motion? Okay, and I want to write down the equation of motion in a relativistic invariant or relativistic covariant way. So I want to write down the equation of motion of the particle in terms of 4 vectors or 4 tensors or scalars, this kind of thing. Okay, so that is the idea. That's why we want to do it covariantly. If we want to do it covariantly, then we better think of this action as a functional of these, coordinates, and we can think of the coordinates as a function of the tau. Okay, tau is the proper time. So let's say, this line, this pink line is the trajectory of the particle. So if this is the trajectory of the particle, then, there's a proper time which kind of denotes every point on the trajectory of the particle. It kind of labels every point on the trajectory of the particle. The proper time is basically the time that the particle, time spent by the particle in its own rest frame, right? So basically, the proper time is basically, in some sense, label for the trajectory of the particle. Okay, this is like, time coordinates and space coordinates. So what I've drawn is literally a trajectory, or this is called a world line of the particle. Okay, it's like the particle, the path traced out by light, the path traced out by the particle in space-time. That is called the world line. Okay, so even if the particle is static, then also it traces out a line because, it goes straight up in the time direction, right? So this is the trajectory of the particle. And so we think of the x coordinate and the x naught coordinate as a function of this proper time, which labels various points on this trajectory. Okay. So with that, and then the action is a functional of these functions, and we basically try to extremize the action by a variation principle, and we try to extremize the action and determine these functions If we determine these functions, then I know what the trajectory is, right? What this world line is that I immediately know. And that is basically the dynamics of the particle. Okay, so that is the idea. And if I now take this thing, and so this is my action. Okay, so I can write this. I can take one of the c inside. So c times d tau. This is proper time. This is the interval, as I have repeatedly discussed. And the interval in the frame where the particle is moving around is basically dx mu, where the mu indices I have carefully written, taking care of this eta here. Okay, so this is the interval for invariant interval for the particle motion in that particular frame where the particle is moving. Okay, so now I have to extremize this action for these functions, where I should treat this. I've just written ds as this object to the power half, because this is ds squared. Okay, this object, I should just extremize. Okay, so these are functions, these are infinitesimals of the functions. Okay, d of this thing, and I have to to the power half, and I have to extremize these functions given that these functions are fixed at the endpoints. Okay, so given these are fixed at some at 2 points here. Okay, at the endpoints, that these functions are fixed, and then that is what you need to find these functions. Okay, so what is that is the usual variation principle. So now how do you proceed? So you can work with this Lagrangian in this form and minimize these functionals. But if you find it uncomfortable that there's this weird to the power half this thing, what you can do is equivalently write this expression. This expression is equivalent to this. You can introduce think of this as a so d of this is basically d of x d tau d tau. Okay, and there are two d taus which you can pull out, and this becomes a d tau outside, tau being the proper time. Okay, and then the integral is from 1 proper time tau 1 to tau 2. Okay, that's the integral. Okay, and of course that is true, because now this becomes the 4 velocity, and the dot of the 4 velocity is basically c squared. Okay, this v mu is c squared, and c squared to the power half is c, and then we get back the same thing. That is true. But here written in this way, we have explicitly the functions x mu, which we want to these functions are the ones that we want to determine by extremizing the action. That's what we want to determine. Okay, so you better keep them if you want to determine them, because we want to vary with respect to them. Okay, so now if we want to vary with respect to them, okay, I do the variation. So I find delta s. So the variation goes in and hits this to the power half first. Okay, that gives me a factor of half. It converts this into a minus half here. Okay, and then the variation hits either this one or this one. That gives me a factor of 2. I've written this one out separately, and then I have put in the variation on the second one. Okay, so this is exactly that I have. I've performed this variation on S and taken the variation inside. It's a functional variation, which I am sure you have seen in your classical mechanics course. Okay, so now if I have done this, then basically now this is in the denominator, so I've written it in the denominator, and because this is in the denominator, in the numerator this factor of 2 cancels, and I have this part. So this part I have written here. Now in the denominator, when it goes, this one, now after I have performed the variation, I can substitute this as c. So I can, this is nothing but c, because this is c square and to the power half is c. So this c cancels this c here, and this becomes minus m, this object here. Okay, where there is a dd tau and dd tau of the variation. So the dd tau acts on the variation. Okay, but we want to write it, for equation of motion, we want to write it as something times the variation. That's how we want to write it, right? So this something times the variation of x. That's how we want to write it. And then this something becomes the equation of motion. So something times the variation of x, and this becomes the equation of motion. Okay. So if so in order to do that, let us use the fact that let us do a total time derivative, tau derivative. Okay, proper time derivative. If I do a total tau derivative on this object, then this object gives me two terms. One term is this, and the other term is this, which I have subtracted. Okay, because dd tau would act on this one to give me this term. It would act on this term to give me this term, right? So this term has the right form, that this is a, the variations have been pulled out, okay, by doing this kind of integration by parts, right? So, and this object here, this is a total tau derivative, and as is usual, if the variations are such that it vanishes at the endpoints, okay, then this is a total derivative. So this is just going to become, this object evaluated at the endpoints, and if the variations vanish at the endpoints, then this is just equal to 0. Okay, at tau 1 and tau 2, if the variations vanish, then this is just equal to 0, and then we are left with this expression, and this expression is nothing but, this is just, the first tau derivative is the 4 velocity, and the second tau derivative is the 4 acceleration, as we defined before. So basically, this tells us that, m times the 4 acceleration, del x mu del d tau, if we integrate it, that is the variation of the action. Now again, setting the variation of the action for extremization, if I have this variation to be arbitrary, then we must have mass times the 4 acceleration equal to 0. Okay. So if you like, this is the generalization of the Newtonian dynamics for the relativistic particle. The relativistic particle should have the 4 acceleration that should vanish, and this has 4 components, mind you. It doesn't have 3 components. It doesn't say acceleration equal to 0. Okay, so if I write it out, then if I write the 4 acceleration out, as I did before also, you see there are these factors of gamma on which the time derivative acts, and therefore because it acts on the gammas, therefore this is a very non-trivial quantity. This quantity is a very, very non-trivial quantity. Okay. So, of course, if in the non-relativistic limit, this is equal to 1, this is equal to 1, and then I have mass times acceleration equal to 0, which is the Newton, it's Newton's law. So that is the thing, that has the right non-relativistic limit. But in the relativistic case, this gamma inside the time derivative, this is very crucial, okay? And that makes the dynamics considerably different from the Newtonian dynamics, okay? And so that is mostly, what I wanted to discuss for this lecture at least. Now, of course, as I said, that these were the spatial directions, okay? That becomes the Newton's laws, okay, if we consider the spatial directions. But this also has the time direction, right? This also has a time direction, the 0, when this mu index is 0. Can you interpret that? Can you, I leave this as a, food for thought for you guys. Okay, can you interpret, what is the interpretation of the time component of this equation of motion that I have written down, in a relativistically covariant way? It is relativistically covariant because this is a relativistic 4 vector. Okay, this is a relativistic 4 vector. It transforms well under relativistic transformations. Therefore, this is relativistically covariant. Okay, so therefore, this equation also has a time component. Okay, the 0 when mu equal to 0, and the question is, can you interpret that time component? What is the interpretation of that time component? Okay, I would leave that as a food for thought. Think about it. What that is. Write it out explicitly and think about it, what it is, and tell me if you can find the answer. Okay, so very good. I will end the video here. In the next video, we will discuss relativistic electrodynamics. Okay, so thanks a lot for your attention. Okay.